Live? I think I'm live. Am I live? Yes, I'm live. Okay. So hello, wonderful people of the internet. Welcome back to another episode of Leos Labs. Again, yet another live stream here on YouTube. For the record, I'm actually continuing a live stream that I just did. Is one continuous live stream on Twitch. I'm trying something new where as I start talking about different topics, I actually do separate live streams on those different topics. So earlier we had a discussion about traditional versus self-publishing. To be honest, I'm just going to see how that conversation goes, what people have to say about that, whether I should leave that video up or not. This stream is going to be more or less a traditional stream. It's going to be the regular old, good old-fashioned Leos Lab stream where we ramble about just about everything we want to ramble about, with the vague notion that we're kind of moving towards discussions on science, rather discussions on analog quantum computing. That's what this is. In the case that you're coming on YouTube, you're watching the YouTube VOD, just going to be clear about that. This is a learn together with me type of situation, not a I'm lecturing you about analog quantum computing situation, right? At the end of the day, we will learn together. It's going to be great. But before that, while we were talking about the self versus traditional publishing discussion earlier, there was a lot of discussion here about Sabine H. YouTube. So for those who don't know, Sabine, again, Hassenfelder, I don't watch her enough that I know how to pronounce her last name, but I've seen her videos here and there, is a science communicator. She is known on YouTube for doing a lot of discussion related to academia, but also just things that she's interested in. And there is a weird, I don't know how to put it, but when it comes to science communication, specifically science communication on YouTube, you gotta be a bit clickbait. You know, you have to. Otherwise, you just die. You know what I mean? Like, this is a similar issue I had with Veritasium, where, like, a lot of his videos just felt really sensationalized beyond the point that I could actually listen to him speak anymore. At some point, he just started saying stuff that, like, is it Sabina? It's probably Sabina. Okay, well, thank you for correcting me. I think you are correct. I think it is Sabina. But a lot of the videos that are coming out from, like, for example, Veritasium, are videos that they were so sensationalized that I could not enjoy watching them. You know, it's one thing if Mark Rober does it, because Mark Rober is kind of an engineer. I kind of get the vibe. But because Veritasium had these videos where he's like, you know, his whole channel is like the essence of truth or whatever, and it just, I don't know. I ended up actually not blocking Veritasium, but I just told YouTube I'm not interested in watching future videos from this person. I mean, the same true for other content creators like Mr. Beast. I do not care what this person is doing, and so I've just kind of blocked them. Not blocked, it's just they don't show up on my recommendations. And I've done that with a few other people. Now, Sabina is not like that. Sabina is a person who actually does have really good, solid scientific opinions. And I do respect what she has to say, because most of what she's saying is completely true. The issue that I've seen with Sabina is not so much that she's saying stuff that's false, or that she's saying stuff that is incorrect. It's that she's incorrect and false are the same statement. I'm being redundant. It's that she says stuff that is kind of conspiracy theory-esque, you know? It enables her audience to kind of bash on academia in a way that I don't typically appreciate, right? I am, just for the record, you guys know, I got my PhD from the Okinawa Institute of Science and Technology, Graduate University. I then worked at MIT for a couple of years. Am I a traditional researcher? I don't think so. I do research software engineering, but I will say the following. I have a, not necessarily positive, but not necessarily negative opinion about academia. There are some things that it does well and some things it does poorly, right? And as someone who's lived through that, I acknowledge what she's saying is not necessarily false, but I also acknowledge that by attacking academia in the way that she's attacking it, sometimes people feel like the entire institution is flawed to a point that it cannot be recovered. And I feel like I'm on the opposite side. Yes, there are flaws, but we can fix these flaws relatively easily, right? Let me jump in with a question. Something Sabina argues is that scientific productivity has been going down and that most papers published are BS. What do you think about that? That's a good question. Let's talk about it. Scientific publishing, let us go. Journal, new page before. We went from self-publishing and traditional publishing to now scientific publishing. So let's talk about that. I'm going to start with the publication economy. So, what is the publication economy? It is a word that I've used a couple times, saying that, how do I put this? You are a researcher, right? That's your job. You do research, right? So this means you put out papers. right? At some point, you have to get paid. Make money from papers, right? That's your goal. You want to make money from papers so you can keep doing research, right? But there's a core problem here in that papers don't make money. If anything, papers will lose money because the way it works in publishing is you spend years of your life doing this study, right? You and a group of people, you and 5 people together have been spending years of your life trying to figure out this one particular thing. You write a paper on this thing. It's a 5 to 10 page paper explaining what it is that you figured out over the past couple of years. You then publish that paper and you have 2 choices. The first choice is to give the copyright of your material to a publisher. That could be Nature, it could be Phys.Rev letters, it could be anything, right? You give the copyright away. The problem with that is that now the paper is behind a paywall. So the only way people can access this paper is by paying for a subscription to that particular journal. That kind of sucks. So nowadays people instead will pay money to make it so that that paper is open access, so anybody can read it. So usually they'll pay like $2,000 or something like this in order to make sure anyone can read the paper. So how much money was it to publish that paper? Let's talk about that. So let's say it was a group of 5 people, so 5 researchers. 5 researchers, let's say for 1 year, let's say times 1 year. I don't know how I'm going to do this. Times 1 year. And let's say they have a salary of $45,000. Times $45,000. Right. Okay, so that's going to be something like, oh, heck, I don't know, 200,000. What is that? $5,000, I think, something like this. Then it costs an additional $2,000 for open access publication fee. And then, right, so this paper, if you add in all the costs, it's something like $200,000 if you take into account the amount of money that researchers make, like the salary. Now keep in mind, I put $45,000 for a researcher salary, which is quite low when you think about it. That's not livable in Boston. You cannot live in Boston for $45,000 a year. And there's certain places in California where you certainly can't live there for $45,000 a year. But this is just the nature of being a researcher. You make less money than pretty much anybody else who has a similar amount of technical expertise. You're giving up on money in order to put more papers out, right? That's literally what you're doing as a researcher. You're saying it doesn't matter how much money I make as long as I'm able to keep pursuing my dream, which is to be a researcher, right? Now, here's the problem. Money doesn't matter in the researcher economy. Papers do. And in order for you to keep making money, you have to keep climbing up the ladder. You have to go from postdoc to assistant professor to associate professor to full professor. It's just a constant ladder with a rung ahead of you at every step, right? And in order to do that, you have to keep publishing papers. So if you go, let's say 6 months to a year without publishing a paper, then you as a researcher are falling behind. You're not taking a step down on the ladder, but you're not moving back up. And you can kind of imagine in the academic world, that there's like a floor of lava that is slowly moving up and up and up. So if you're not climbing up this ladder, eventually you're going to be kicked out because you're too old to do research or whatever reason. There's so much competition in the area. So many people, like, their dream job is to be a researcher, that you've got to keep moving. And if you don't keep moving, you're going to die. So what ends up happening, or die in the field, not like literally die, you have to leave academia, right? And so what people end up doing is they end up publishing more and more papers that are kind of not exactly great papers. Sure, they still do push the boundary of human knowledge, but in ways that are so small and insignificant that probably nobody cares, right? And now there's a huge economy created specifically to keep all these researchers up and afloat, to keep them walking up the ladder so that their dreams don't die, right? And so you have this thing where people are constantly putting out more papers than people can like properly review. And because there's too many papers and not enough people to review those papers, because again, no one pays reviewers, right? So this is also just something you do in your free time on weekends. It makes it so like the whole thing is just popped up by basically goodwill. And it's entirely possible that a couple papers are crap and they are published simply for the sake of padding out someone's CV. People spend a lot of taxpayer money on it. Again, we're talking about $250,000 potentially for a paper. For what purpose, right? It doesn't actually do anything meaningful. It wasn't actually reviewed properly, and it goes out for basically a couple people to cite for no real reason, right? So this is a publication economy. It's basically a way to keep researchers afloat, and it's something that people need in order to advance their career, because in this field, money doesn't matter, but papers do, right? That's what I'm trying to say. I saw someone saying something like that, but measurements of productivity seem questionable. Publish or perish. Yeah, exactly this. Publish or perish. That's exactly what I was saying. It is a circular problem. You need money to put out a paper. Speaking about floating, it is a flood of poorly thought papers. Exactly. So let's talk about this. Now, there was a discussion here about scientific productivity has been going down. So how do we measure productivity? What does that mean? Right? And let's talk about that. What is scientific productivity? Question. What is it? I don't know. I have no idea. This is one of those things that you cannot define. What does it mean? So you could argue, for Sabine, this is actually very important for her because she worked more or less in theoretical physics. She's trying to argue that there hasn't been a large, scientific discovery on the order of general relativity or something like that in 50 years, right? That's the argument, right? But you could argue, yes, we have had those, right? What about AI? What about the internet, for Pete's sake, in the last 50 years? What about all the advances in CG? Like, we're talking about literally everything to do with GPU. I mean, sure, okay, you could argue that in physics itself, it is not moving as fast as she would like. But to say there is no scientific productivity is ignoring the fact that we have huge advances in other fields. Like, what about the Human Genome Project? What about in physics itself? We have the boson, the Higgs boson. What about all the space stuff? We're talking about black hole visualization. We're talking about, there's so much stuff that's been happening in the past 50 years. To say that we're not as productive as scientists because this one particular field is not advancing as fast as the other fields is to ignore the fact that the boundary of human knowledge is still advancing at a rate that I would argue is incredibly fast, right? Really, really, really fast. People can't keep up with how fast it is. This is why you have all these crappy journal articles coming out or crappy news reports coming out saying scientists have recently discovered that, I don't know, chocolate makes your baby fat or something like this. It's like an incredibly obvious thing, right? And the reason they have to go so far down, basically they have to explain to elementary school students some incredibly controversial study, right? And explain why it's controversial. And so the only way they can get people interested is if they talk about it in such a way that they make everybody click because they're angry. But actually the paper itself was about something really important, right? So there was a discussion that happened the other day talking about how there was a couple papers coming out. I don't remember the exact words, but giving antidepressant to drunk flies, something like this. I don't remember the exact thing, but basically there was some people on Twitter who were upset that their tax dollars were going to giving antidepressants to drunk flies, something like this, a fruit flies, something like this. Fair enough. Some taxpayer money, I think, went into this study, right? But the reason it went into this study is because we can't give antidepressants to drunk people, right? That's against human ethics. We're not able to do it to real people. So we find an analog animal, which happens to be a fruit fly for this particular situation, and we say, okay, here's what we're going to do. We're going to make them drunk. We're going to give them antidepressants. We're going to see how this affects their livelihood. This should, in principle, help, let's say, veterans with PTSD or something like this, right? And so what ends up happening is if you go online, you see all these studies like this, which are taking results that are massively they're taking results from a very specific study with very specific goals in mind, right? And they're turning it into something that fifth graders can understand. And then you have some people coming in and saying, well, this is a stupid study. Why would anyone do that? Without realizing that the reason they had to dumb this down to this extent was so you could understand what they're doing in the first place. What they could have instead said was, we're trying to tackle PTSD and stuff like this. You know what I'm trying to say? There's a whole bunch of different ways they could have said that, but people wouldn't click that. They would click giving antidepressants to drunk flies, Let me catch up on chat. She says the technology used today is based on physics made 100 years ago. I do somewhat disagree with that statement, but I understand where she's coming from. But I would consider reaching a plateau and not going much forward. There should be, Marion, scientific productivity. I really think it depends on the field. There should not be that if there are no paradigm shifts, which are rare according to Kuhn. tell me more about what defines a paradigm shift. Maybe I don't understand. I think most of the claims that academia has been underperforming come from the fact that string theory has far underperformed compared to what it has promised to be. What? Who cares about string theory? Genuinely, who cares about string theory? I know there are string theorists who care about string theory, but who beyond the string theorists care? You know, like, I don't know a single scientist. I don't know a single academic besides people who study string theory who even believe string theory is a valid theory to describe the universe itself. Like, this is not something that people are like. Most physicists I know do not believe in string theory. You know, like it's one of those things where, like, until we have some shred of even a possibility to experimentally validate a theory, it's really not worth spending as much time on it. You know, people can't grasp how few drugs you need to feed a fly. I mean, it doesn't make much to get a fly drunk. This is fair, right? To be fair, general relativity. You removed a message. I think I already responded to that. And quantum revolution are hard bars to beat. Yeah, but I do understand what you guys are trying to say. That, like, okay, but in terms of physics, right? In terms of physics, if we only think about physics, what's next, right? We had the quantum revolution. We had general relativity. What is next in physics, right? And we have all these sci-fi, you know, things. We have, like, teleportation, and we've got, like, faster than light travel, and we've got, like, the, I don't know, space elevators. We have these things that we're trying to build up to, right? But I just feel like, okay, maybe I'm misunderstanding what the shtick is, what we care about here. But I think it's okay to have a field, specifically physics, that kind of doesn't quite advance as fast as other fields, with the assumption that other fields are still expanding. I mean, look at climate change, for Pete's sake. Like, you could argue in the past 50 years, sure, okay, maybe the actual physical principles, we haven't evolved too much. Like, maybe string theory isn't, like, as developed as it could be. Okay, fine, fair enough. But on the other hand, we've made really, really fast and rapid strides in so many different areas. I don't know. I would not say scientific, like, academia is underperforming at all. If anything, I would say, I mean, in the past couple of years, I mean, like, you see people walking around here in Barcelona with NASA shirts. You know what I mean? Like, not only is science, like, normalized, but it's so mainstream that people, like, kind of care about the results. And I think that's really good. I don't know. I do understand the argument that it is not, certain fields are stagnating, and I think that is probably true. But I think the general vibe is quite positive. It's when a field stops its usual puzzle-solving activities because they get sick of firing their researchers for failing to solve their puzzles using their current paradigm, so they adopt a new paradigm. I guess that's fair. I don't really know what would be considered a paradigm shift for physics. I guess you're right in that, like, quantum physics could be considered a paradigm shift, right? Because you know, we did so many things to validate whether, you know, quantum physics makes sense, you know, like, heck, 100 years ago was the Michelson-Morley experiment, right? 120 years ago or whatever. And people were thinking at that point that there was, like, this ether, this goop that we all lived in, and that light somehow propagated in this goop. And the reason they thought that was because, otherwise, like, it wasn't very clear how light could act as a wave at all, because, you know, if something is a wave, it has to wave through a medium. Like, we're learning stuff, you know? It's just, I think in Sabina's specific field, it's not moving as fast as she would like. With how little science funding is, I would say academia has been extremely productive. Sad that the new U.S. department threatens governmental waste. Yeah, this is not a political stream. But let's talk about that. Let's see if I can find a particular plot. Which country spends the most on R&D? Israel. Interesting. Spending leads the world in R&D spending as a percentage of GDP, followed by South Korea, US, Japan, Belgium, Sweden. Right? Now, you could argue, oh, US is number 3 on the list. It'd be so much nicer if we were, like, number 1 on the list. But if we're number 3 on the list, behind South Korea, right? We're doing pretty well considering our GDP is so high. You know what I'm saying? Like, I understand what you guys are saying. You're saying that, okay, it sucks that we are in a situation where certain governmental leaders are threatening to drop research funding in certain areas, right? And that does suck. Part of the reason the US has been on top for so long is simply because they spend more on research than any other country. And because they're spending so much on research, we have a brain drain where we literally steal the smartest people from around the world, bring them into the US to do research, right? It hurts everyone else's economy, but it's really good for the US, you know? And so in the next 4 years, okay, maybe we don't spend as much on research. Maybe we give some research areas to other countries. By we, I mean the United States. But as a globalist, I don't know if I'm actually a globalist, but as someone who appreciates or feels like, you know, the world would be better if everybody does research, not just people in the United States, maybe at the end of the day, increasing the research budget outside of the US could be helpful. And I think most people have acknowledged that you need smart people doing smart things to move the economy. You need smart people doing smart things to move anywhere, to do anything, right? And so I think it's not all doom and gloom is what I'm trying to say. It's not all doom and gloom. You could do a react to her last 20-something minute video. She addressed some things. My understanding is that she's criticizing the way science is done. In addition to its accomplishments, she fears what she sees in her field spreads to other fields. That could be fair. I'm going to get political. Wink, wink. I'm not going to get political. I don't feel like what I'm saying here is too political. I'm just mentioning facts here, I feel. Like, okay, look. The other thing that I really want to mention, there was a plot I saw. I'm going to see if I can find this plot. I can't quite find the plot. This one maybe is what I'm looking for. Yes, I think this is the one I'm looking for. So percent in total R&D of total discretionary budget, non-defense R&D of total non-defense discretionary budget. So this, I believe, is U.S. Federal Scientific Research and Development Budget Overview. Okay? So what are we looking at? So we're looking at the 1960s. We're literally spending 25% for R&D, right? To be honest, I don't exactly know what these metrics mean, right? So I don't know exactly what discretionary, non-discretionary means, but my belief is that discretionary is what is available to the President of the United States, and the other bit is what's provided by Congress, right? So we see here we're spending a heck of a lot of money on R&D in the 1960s and 1970s, and you might be asking yourself, why are we spending that amount of money? Obviously, the Cold War, right? I mean, that's obviously what's happening here. Literally, it was just a measuring contest between us and us being the U.S. and Russia, trying to put as much money into research to get as much research out there, because that was how they measured the success of their countries, right? And so during this time, we see a huge amount. I mean, I dare say this was the era in which people want to make America great again. You know, this is the era that people think about when they think about American greatness. Now, was it actually great? No, we spawned so many wars all over the place. Our international policy was a mess. Look, I'm not going to sit here and pretend that the U.S. is a good guy here in all ways, but at this time, the U.S. economy was doing really well, and we were doing super well, in part because of research funding, and also in part because of post-war boom. Now, you'll note that this drops off, right? And it's plateaued, right? So let's see what happens at 2016 during Trump's last presidency. We note that the discretionary budget drops, but the amount that Congress is spending, the non-defense R&D and total non-defense discretionary fund, it stays consistent, right? And so, sure, okay, we're losing a couple percent here. It comes back up under Biden in 2021. But let me see if I can visit the site. But for the most part, I don't think we're going to see a huge radical shift in the amount of money that we're spending on the budget. I think it's going to remain roughly the same. It might drop a couple percentage points, which does mean a lot of people's jobs. But I don't think it's going to be as radical of a change as it could be. You know, I'm coping, but I'm hoping that it's not that bad. There's a toy problem called research versus exploit, where you divide resources between doing research versus exploiting that research, like trying to learn what the payouts of various slot machines are versus using that knowledge. Right. This is, it's a very difficult problem to get right. But it is, research helps so many different areas. It helps out the education sector. It helps out, the development sector of particular products. Like, basically, doing research is always a net good. And for the longest time, for years and years and years, every single Congress member knew the value of research, right? And we even there was a time when the U.S. literally paid half of all scientific funding. And I think that's almost true today. I think, like, if you look at the worldwide amount of money that people are putting into, like, dollar per dollar, putting into research, I think the U.S. is still on top. I think it's second place to China now, but it's up there, And we need to, I mean, we need to keep that going. And I think most people acknowledge that they need to keep this going. Once they see it as an arms race against like China or something, all of a sudden, all bets are off. People are going to spend money in the US again. Sabine, have you taken a look at Unzicker Real Physics? He takes things a step further. I haven't, actually. Maybe I should. Exploration Exploitation Dilemma, right. Maybe they are talking about making a large change to that. Well, now they are researching what used to be a UFO. Tell me more about this. I want to learn more about this. What do you mean they're researching what used to be a UFO? I don't know what you mean by that. Since its peak in 1960s, due to the Apollo program, total federal R&D spending has been consistently 10 to 12% of the overall discretionary budget. Light blue, federal non-defense R&D spending has followed a similar trend in comparison to the total non-defense discretionary budget. Orange. Sure. My point is that let's just look worldwide. Oh, maybe it's here. Maybe I can already find it here. World map of sovereign states by research and development spending per capita, according to. Why is it? What is up with? Am I the dumb one here? Like, why is it? Why is it this way? What advantage is there for drawing this graph like this? Am I the weird one here? Like, am I the one that's maybe a bit? Okay, maybe I shouldn't be like, how do I put this? Maybe I shouldn't be upholding like, weird. I understand that the normal world neck, I understand that the world map that most people typically see is already very biased, in terms of like landmass and stuff like that. But this feels, okay, anyway, it's fine. I don't care. It's fine. I don't know why they did it that way. So world map of sovereign states by research and development spending per capita, according to OECD. The U.S. is always going to be one of the top spenders there. What I want to see is the amount of money. Gross domestic research and development, percent of GDP. I don't want percent of GDP. What I want is the amount of money that they're actually putting in. And I don't know if I can, maybe, no, that's percent of GDP year. Oh, maybe million of US dollars is what I want. Okay, so US is still, is it? This can't be right. Gross domestic spending on R&D. Is it really 700? Okay, I mean, look, I really thought China was, because it's not in this map. Because this is only of OECD countries. Ah. No. Where's China? What is an OECD country? As Organization for Economic Cooperation and Development. No, China's definitely going to be here. Am I just dumb? What? Where's China? Is down here? No, that's not right. Oh, what? I don't know what I'm looking for. What projection is that? Just a different projection that favors equatorial region instead of the north. That's fair. In principle, this should be the more common projection probably. Trelsinger, thank you so much for following a few minutes ago. You do not typically travel through the Arctic or Antarctic, but maybe with climate change, I guess. Yeah, to be honest, in one of the books I was writing about people living on Point Nemo, I actually talk a little bit about how the how travel will change in the next 50 years due to climate change. And going through the North Pole is one of those things that is going to change a lot of stuff, I think. I think both Canada and Russia are going to be prime real estate in the next 50 years. Might be opaque into China. I think that's what's happening. I think we're just not showing China's budget. But the fact is, compared to these countries listed here, US is still on top in terms of just the sheer amount of money that we're putting into the system. Again, a few years ago, like literally the amount of money that the US was putting in to research was equivalent to every other country combined. Like literally half of all research spending was in the US. Like compared at every country together, right? And that was equal to the amount the US alone was putting in, right? That's the difference in spending here. And so a couple percentage points, yeah, it sucks. But I'm hopeful that it's not going to be like all budget. You know what I mean? Besides, if you really want to be efficient with government spending, probably the defense budget is the number one thing you have to cut out, not cut out, but like drop, because there's a lot of mishandling of money there. Applies a Mobius transformation of the globe for no reason whatsoever. I think the map like this is divide the global south and global north. That's probably a fair point. Uh, a couple percentage of a very big pie. That is also true. It is a very big pie. You drop this a couple of percentage points, and now you've dropped essentially a couple percentage points of the entire spending in the rest of the world as well. That's huge, right? That is huge. Yeah, and just keep in mind, like, there's a whole bunch of people who think that researchers are just like paid like a whole bunch of money to do their research, and they're not. I mean, researchers don't get paid that much at all. It's not like basically barely surviving type of money. Not exactly like, you know, you could argue they get like cashier level money, maybe a little bit more depending on where they're at. Specifically, if they're like a postdoc. Obviously, postdocs are not paid that much. They're basically paid minimum wage, but professors generally are paid okay. You know, they get about $100,000 per year, which is fair considering the amount of work that they put in for the most part. Some professors don't. Some just do teaching, and that's fine. But the professors who are doing research as well, I mean, there's a reason why when you email your professor at 2 o'clock in the morning, they will respond at 2 o'clock in the morning, because they're also up and doing work at the same time. You know, it's just kind of remarkable how like a lot of people who don't like college spend time like just, you know, saying their professors are awful without realizing the amount of time and money, or the amount of time and effort they're putting into not just the classes, but also to the research that they're doing. Like, that's the majority of what professors are doing is usually research. And that's where they're spending their time. And that's also what makes the universities money, because they get the money through grants and stuff like this. Anyway, rambling upon rambling upon rambling. Let's go back to the science communication discussion. I don't like watching videos on stream because for me, it's not compelling content. I don't like watching, I don't like watching videos to begin with. And so watching them on stream is kind of like another level of me just feeling awkward in front of people. And it's why I don't typically do it. I tried it last time on the Analog Quantum stream, and it was the first time I'd ever watched a video on stream to react to. I'm not willing to do that again. But if there are cliff notes, or if there's a script or something I can look at, I'm more than willing to look at that. 1 second. What button am I looking for? This one? Sorry, I had to cough a little bit, and I didn't want to cough in front of the microphone. So let's talk a little bit more about science communication before going on to the discussion of analog quantum computing, because there's a lot of stuff that I still want to talk about. So for the science communication discussion, the fact is that we're in a radically different era than we used to be for science communication. And this is something that I've been grappling with. I feel a lot of people have been grappling with. And I'm going to say the following. I think, and of course I'm very biased here, but I think in this day and age, your science only as good this is what I believe. Your science is only as good as your ability to communicate that science. By this I mean, sure, you can do like literally, you know, you can push the boundary of human knowledge in many different ways. But nowadays, because it's so strict and it's so hard to get research funding, even if your theory, your idea, your experiment, whatever it is that you're doing, literally is the most groundbreaking thing to have ever existed, you have to be able to communicate that science not only to the funders, but also to everyday citizens. And if you're unable to do that, then it's not that you're failing as a scientist, but you are potentially not... I just feel it is a scientist's duty to be able to describe what you're doing to a 5-year-old. I really think you should be able to do that. Even if it's just very simple, being able to describe your research to people is a key and integral component of not only of doing the research, but motivating people to do research in the future, right? Part of the reason NASA was so big and the space race was so big is because everyone on Earth knows what we're doing. We're going to space, right? That's easy. Everyone's wanted to go into space at some point. They've wanted to see what's out there. This is so easy to motivate people because it's so easy to say, this is what we're doing. This is what we're funding money on. There's you know, another group who's trying to do it as fast as we are. We want to show that we're better. Like, it's a very easy narrative to sell, you know? And finding that narrative of your research to sell to people is incredibly important, because if we as scientists lose sight of the fact that we're also storytellers, we run into a situation where everyday citizens have now lost the plot. Everyday citizens see this and they're like, what are we spending our money on? Why are we doing this? And they don't see the researchers, the people who are constantly publishing papers. They don't see the people behind that research who are incredibly motivated to make their own breakthroughs and to change the world as we know it based on the discovery of this random paper. You know what I mean? Like, we have to show people that there's not only science happening and good science happening. But that good science is also pushing boundaries in ways that are exciting and interesting and not just giving antidepressants to drunk flies. You know what I mean? Like it is interesting in its own right, and being able to present that information in such a way that people find interesting is very important, right? It's why, like, it's why I'm doing this stream. It's why I've tried to explain my research in the best way I can. It's so important to let people in and to see and to show them why the thing that you're doing is interesting. Like, this is so important, and it's such that it's one of those steps that a lot of scientists don't do correctly. You know what I mean? Well, funders care about how you market what you found, and people care about what benefits them their daily life. It's somewhat easy to understand a problem. Solving it is always a drag. Yeah, but honestly, solving a problem is also quite fun. Like, if you're a researcher and this is what you do, I mean, it is enjoyable, right? Like, I mean, I genuinely love the feeling of sinking my teeth into a difficult problem. It's why I love reading research papers. It's why I actually really love writing poetry as well, because it gives you that feeling of like that. It's like solving a puzzle without having like stakes to the puzzle. That's what poetry feels like for me. And it's quite enjoyable for this reason, and writing papers is the same thing. It's really enjoyable because I feel like I'm presenting information. I'm putting everything together. I'm telling a story. It's quite fun. You know what I mean? And, I just wish I could show more people that enthusiasm I have. I got an article with a lot of pro-con presentation charts of analog to digital. Yeah, go ahead. Let me see what that is. Int82, thanks for following. I will say on Discord, we had some discussions already. And how do I put this? I've got questions, right? So first of all, I took classes in analog computation and I guess digital computation because everything's digital. But yeah, analog computing is one of those things that like I know a lot about from the classical perspective. But from the quantum perspective, I'm not entirely sure what it means. Marketing to both sides, the manufacturing and the buyers, right? Let's do a copy link, paste it over here. I accept. I have no idea what that is. Unbelievable zombie comeback of analog computing. Okay. I'm already a little bit upset at this title because analog computing never went away. If people are arguing that it went away, like, I don't know what they're talking about because, okay. Also, why would you ever listen to the story if you have the text down? If you have the text down here, like, under what situation would you want to? Sorry, I'm opening at Firefox because of the ads. I still have ads. uBlock, please. Why? Oh, no, just there. Okay, good. Whew. All right, let's go. All right. I am like, I like listening much more than reading. Okay, yeah, I'm obviously the old man in the room, right? Okay, when old tech dies, it usually stays dead. No one expects rotary phones or adding machines to come back, crawling back from oblivion. Floppy diskettes, VHS tapes, cathode ray tubes. I'm gonna ask something stupid. I'm gonna ask something really, really stupid. Really, really, really stupid here. But like, are FPGAs analog? Like FPGAs, right? Can't you consider them to be analog? Like, am I dumb here? Or is this not true? No, I'm completely wrong here. I just didn't know what an FPGA was. I liked FPGAs when I was in college, but my career took me down the path of circuits. I love it, but also constantly find myself drawn to FPGAs. What is an FPGA? I know it's field programmable gate array. I know you can code it in OpenCL, but I don't know what it is exactly. I like listening much more than reading, and I can put it 3 times speed, which is 3 times, which is much faster than I can read. Yeah, I guess because I usually speed read. Like, that's actually one reason I don't usually like streaming too much. Like, when it comes to like doing research and stuff, because it's so much slower to read it aloud and to explain it to people. But again, that speed is, I don't know, it's worth it to communicate. So I don't know. Gate array means transistors. See, I already learned something, right? Any digital thing is ultimately made of analog stuff. There are things called field programmable analog arrays. I see. Okay, fair enough. Yeah, right, that's the other thing. Like, when you think of transistors, right, exactly what I think. Any digital thing is ultimately made of analog stuff, right? That's what I typically think of. I think you use some digital mechanism to do the patch wiring for you. FPGA is basically breadboard, but in chip form. That's what I thought as well. But I guess but in chip form makes it so it's not analog. Fair enough. Let me go ahead and scan through this. So for example of how digital has displaced analog, look at photography. In pre-digital cameras, continuous variations in light created chemical reaction on a piece of film where an image appeared as a representation, an analog of reality. In a modern camera, by contrast, the light variations are converted to digital values. These are processed by the camera CPU before being saved as a stream of ones and zeros, with digital compression if you wish. Okay, analog. Calculation using various values. I want to see quantum. Tell me where the quantum comes in. I understand the difference between analog and digital, okay? But where's quantum? Okay, I asked him whether the state of analog computing today could be compared to quantum computing 25 years ago. Could it follow a similar path of development, fringe? All right, keep going. Oh, quantum. No. This is quantum computation. Okay, I don't think they cover quantum much here. Okay, so what are they talking about then? I thought they were talking about how analog computation is coming back in quantum circuits, or something like this. But this isn't about quantum at all then. That's me being stupid then. So where is it coming back then? Man, this is why you need an abstract. That's all. I just want an abstract, you know? Let me get a temperature read from you before we leave the subject. What are the percent of published paper you'd be considered BS? Oh, you're right. I didn't actually directly answer that question. I'd consider like maybe 5 to 10%. And let me explain. There is this thing, right? There's this thing. The replicability, right? Replicability crisis, right? Replication crisis. Amos Veritasium made a video a few years back about analog computing making a comeback. Yeah, so I just never knew it left. So now I'm confused as to how it's coming back when it never left. You know, like that's what that was why I'm questioning. Like what specifically is it? What does it mean, right? Like what does it mean to come back? What areas? Yeah, more information. Okay, so let's talk about the replication crisis. My question. Let's go in here. There is, in psychology, there's this thing, right, where a certain number of papers cannot be replicated depending on the field. I'm looking for a very particular graph here. How do I put this? It's a high number too. It's like 50% or something like that. Oh gosh, where's the paper I'm looking at? So let's just read this. So the replication crisis is an ongoing methodological crisis in which the results of many scientific studies are difficult or impossible to reproduce. Because the reproducibility of empirical results is an essential part of the scientific method, such failures undermine the credibility of theories building on them and potentially call into question substantial parts of scientific knowledge, right? VSI devices that use something like potentiometers to multiply and current junctions, Kirchhoff, to add matrix multiplication. Oh, they're doing matrix multiplication. That's interesting. That's quite interesting, right? Are they talking about creating like new chips specifically for like ML devices? Because again, this is quite interesting. The replication crisis is frequently discussed in relation to psychology and medicine, where considerable effort has been undertaken to reinvestigate classic results, to determine whether they are reliable, and if they turn out not to be, the reason for the failure. Data strongly indicate that other natural and social sciences are affected as well. So let's talk about this, right? And let's talk about it from the perspective. Let's first talk about the perspective of how this looks from the outside, because that's the most important thing, right? So there are a whole bunch of people who are claiming that academia as a field, as a concept, is fundamentally failing, and part of that failure is coming out in the replication crisis. And I do agree with the statement, right? Like, it sucks that there is a large number of papers. I don't know the number here. I'm trying to find the number here, but it's something like 50% of papers can't be replicated in psychology or something like that. Let me see if I can find more information. But let's just take it at face value. A large number of papers cannot be replicated in certain areas, right? That absolutely sucks. And part of that is because people are rushing to put out papers because of the publication economy that we talked about before, right? They have to put out papers in order to keep going with their career. They publish or they perish, right? That's what it is. Now, with that said, I am not as doom and gloom about this as I was a few years ago. So a few years ago, when I was finishing up my undergraduate, people were talking about the replication crisis. They were talking about how, like, papers can't be replicated, which means a core element of the scientific method is just failing us. And that's true. This is all kind of true. But another part of me feels like I've never read a paper that I feel is necessarily bad, right? And let me explain what I mean. There have been several papers that I've read that the results are questionable, right? Very questionable. And in fact, I then asked the authors for some sort of code or something to go along with the paper. And I realized that the code is actually different than what the paper intended to show, right? And so basically the paper says one thing, but the code says something else, right? This is why it's a very good idea to make sure that your code is always available for the paper, as you cite the code along with the paper, blah, blah, blah. But this paper didn't do this. It was from a different era, blah, blah, blah. So in this case, you could argue the paper was crap. It was a complete lie. It was fabricated. It was false. On the other hand, reading that paper for me as a researcher helped me, right? It allowed me to explore an idea that I would not have ordinarily explored, and that connection between these two fields that were ordinarily completely different has allowed me as a researcher to learn about a different field that I would not ordinarily learn from. And not only did I learn from a field that I wouldn't ordinarily learn from, I also now have the ability to I can use that knowledge in a future paper. Can I use that exact result? No. This is why every time you read a paper, you have to do your due diligence and make sure that the paper is actually, correct. You can't just read the headlines and assume that is 100% correct. But if you're a good scientist, you're not doing that anyway, right? You're not going to just read an abstract and say, yep, that sounds good. You have to read the entire paper. You have to read the methods. This is what you do. This is your job as a researcher to do that, right? And so, sure, there are some papers that are wrong, and in that way, they are BS, right? But I don't know if I necessarily feel like I'm a worse scientist for reading them. You know what I mean? I don't feel like it's worse that, this paper exists, and it helped me learn something. Therefore, I don't necessarily feel like it's that bad. I'm very biased here, but I don't feel like it's as big of a deal as, for me in particular, as a lot of other people. Let me catch up on chat and let me kind of ruminate on this a little bit. But they don't appear to be great for training. But if you train using a digital device and then take the weights and put that into an analog device, it could be advantageous, right? That's totally fair. For example, for a lot of the quantum experiments, or not quantum experiments, but for some of the studies I've done before, exactly what you do. You have some sort of digital thing, and then you do an optimization on an analog thing so you can get that actual precision. We need more data, and this is where I take issue. People won't publish when they fail. A bunch of people will fail in the same way, and nobody will know. Right. This is also another thing. I wish there should be a journal for failures, right? The journal of failures. Is there a way to turn that into a catchy title? Probably. Psychology was written with Freud's and Jung's almost all unproven discredited hypotheses, especially IQ. Don't forget Francesco Gino. Is this actually live? It is live, yes. If you guys have questions, comments, or anything like that, feel free to ask. I'm switching between Twitch chat and YouTube chat. It just happens that Twitch chat has been more active, so I've been kind of more or less on the Twitch side, but I go back and forth. Annals of Improbable Research. Oh, that's pretty good. That's pretty good, though. What I was going to say is specifically with psychology, right, and these more soft sciences, yeah, the replication crisis is insane in these areas, right? It's one of those weird situations where, because I'm coming from physics and computational stuff, I'm doing computational stuff, it is, it's not as big of a deal if I'm wrong, right? Or if this paper is wrong, because it's relatively easy to validate the paper. I can just run the code. I can look at the code. It's much easier than performing a new experiment where I have to collect 100 different people, and these 100 different people all have to be white male. And not only do they all have to be white male, they have to all be about the same age and have been in the same social area in which they could understand this particular phenomenon. And there's so much that has to go into doing these psychological studies that it's almost impossible to replicate a study to begin with, right? And so in my mind, there is basically no company who will use the result of a psychology paper and just at face value, right? what they'll do is if they really, really need that result, they will replicate the result with in their own way before actually using the result, right? The other thing to keep in mind is even if a couple papers are wrong, that's okay, because a lot of ways science moves based on consensus, right? Like it's generally we're trying to figure out how to discover or learn about this particular thing, right? We don't know what this particular thing is, but we're trying to learn about it, right? So we do a whole bunch of experiments around that thing. We tiptoe around it, try to figure out this and that. And as we're tiptoeing around it, sure, some of those steps are missteps, but at the end of the day, we're figuring out this thing together. And so there might be a whole bunch of papers that aren't quite right. And if you look at them with with a modern lens, you'll think, oh, this is absolute garbage. But they existed at a time, and they pushed the boundary of knowledge at a time in a way that had not been pushed before, hence why you're reading it to begin with. And in that process of pushing that boundary of knowledge, you enabled researchers to take another step in another area, right? In a lot of ways, like these papers that can't be replicated, you can kind of think of them as like, ideas or like theoretical proposals for something that could be happened with light justification for that thing. And in some sense, having that discussion is worth having, So this is why, like, a lot of people are like, oh, all scientific papers are junk. I completely disagree with that statement. I've only read like a couple papers in my life. I've read a bunch of papers, and I've only read a couple of them that I feel are genuinely wrong, right? And for those papers that are wrong, even reading them taught me something that I didn't know before. And so even then I can't say that I'm a worse person for reading this wrong paper. You know what I mean? I don't know. So my percentage is quite low. I'd say maybe like 10% of all papers, like taking into account the social sciences, are bad, I would say. Even if a lot of them can't be replicated, this doesn't matter too much to me. But I do understand from outside, people are using the replication crisis as a way to attack academia and say that the entire system is failing. And in some ways it is failing, but not necessarily in this way, in these ways, I would say. Anyway, I'm really like, I don't know what I'm talking about. What about those papers where researchers themselves know it's a hoax, but it's to meet a quota to make more money? These do appear from time to time. My hope is that they don't happen that often, right? So for example, the vaccines cause autism one, right? Like this, I don't know if it was necessarily a hoax or not, but it was very clearly discredited, And yet people are still running around saying the vaccines cause autism, even in 2024, even though that paper has been withdrawn and wasn't even a significant, wasn't even a significant result to begin with in terms of like the amount of the correlation between the two ideas and everything. It's just one of those things where like, I don't know, people are going to put out crappy results. The conspiracy theorists are going to take those crappy results. If they like the crappy results, they're going to say, this is great. And they're gonna run with it. It's gonna become like, this paper is like the only one that shows the truth or something like this. You know what I mean? Like, just because there's a whole bunch of people who are really, really worried about the scientific process because of the replication crisis, they're fair to worry about it. But it's also like, the problem I have is that this particular topic is one that there's so many people who are just arguing and bickering about how science is flawed because of it. And it's like, for the most part, I see it still working, right? This is why we have so many people replicating different results with different experiments, if like paper A is wrong and paper B relies on paper A for some experimental study, well, then you're going to find paper A is wrong when you're doing paper B, right? Because it relies on the results of the previous paper, in order to show something better. So like if your paper is being built upon in a way that also advances the boundary of human knowledge, you'll figure out that paper is garbage pretty quickly when other people can't use it, right? I don't know. I have a lot of thoughts here, and I don't think they're really making any point. What about those papers? So failure is an option. My general idea or my general thought on those papers that are definitely a hoax and people know they're a hoax to begin with, is it's actually quite difficult to do well. Because again, if papers rely on the results of your experimental study, let's say, you really have to fake that data in such a way that it's like very nuanced, because otherwise people who are building upon your work will immediately see it's not correct, right? Because that's the thing, right? No science happens in a vacuum. It's all built upon other papers that were built upon other papers that were built upon other papers. And so if part of that foundation is weak, you figure that out as you start building on top of it, and things become clearer pretty quickly. That's why the scientific consensus matters, right? I was reading something. Wait, failure's an option. Adam Savage, DEFCON 17. Isn't Adam Savage the MythBusters guy? I was reading something somewhere where they were figuring out how much it would be a good idea to drop the device voltage and deal with errors. That's fair. We're talking about the analog versus digital stuff. There's something that is still not clear to me. Sabine describes how some particle physicists make up particles and hope to them with an accelerator. Yeah, I'll read that in a bit. Econ is even worse in my opinion. I still remember one professor got mad because he didn't want to do sensitivity analysis. Wakefield's paper is already questioned in the same journal issue by a reviewer. The rabbit hole is very deep though. Yeah. To be honest, maybe I'm just not... Maybe I'm unnecessarily hopeful. Maybe that's what it is. Maybe I should be more like critical and stuff like this. It's just as someone who loves reading papers and loves writing papers and loves doing research, I just... Again, maybe I'm too deep. Maybe I've drank too much Kool-Aid. Maybe I'm just like too far in the cult to really, let these issues let these issues impact my willingness to do research. You know what I mean? Like, how do I put this? Part of the reason I'm streaming, part of the reason I'm talking to you guys about this, part of the reason that I'm out here, and not just reading papers and writing and doing all that kind of stuff on my own, is because I do genuinely feel there is utility in being open about this type of stuff and being transparent and talking about all this kind of stuff. And like I said before, scientists are only as good as their ability to communicate their research, and I feel like we're missing that direct connection between researchers and people, And if you add that connection back in, all of a sudden these conspiracies about the replication crisis, not conspiracies, but all of these issues, that are causing people to distrust the systems in science start going away. Like, this is what you need. You just need someone out there talking, doing their research, showing the world what they do, why it's interesting, all this kind of stuff. Like, basically, once you start doing this, all the other boundaries start falling down. And then I don't mind people talking so much about the replication crisis. It's a big deal. It's something we really need to talk about. But in talking about it in a public space where there's basically no researchers actually talking about it as well, it turns into this one-sided argument where everyone's saying, oh yeah, this is why we shouldn't fund research. But that's obviously not the result we should pull from this. The result we should pull from this is that maybe we should force journals to have a much harsher review structure, right? My personal opinion a while ago was just to say, look, we don't publish any papers. We create a journal whose sole purpose is not to publish anything unless that thing can be replicated in the journal's specific laboratory, right? That's what I would say, right? So when people apply for funds from the US government or from wherever they're getting funds from, they apply for, let's say, 50% extra funding so that they can prove that the reproduction is happening in a independent laboratory, right? That would be, in my opinion, the number one way to deal with this. Just to say, look, every paper requires not just one experiment, but two. Does this slow down the publication economy? Yeah, it does. Does this mean we have to figure that side of things out first, right? So figure out the publication economy, right? Figure out how to make it so people don't need to consistently publish so many papers and they can relax and take their time with each one. Then solve the replication issue. And by solving the replication issue, just get extra funding so we can have an independent lab do the replication of every result. And while that replication is happening, sure, that specific research group can keep going and publish other things as well. I don't know. There are solutions here. It's just that it's all kind of mixed up together. So one really positive thing that, for example, Biden did is he said that any papers that are published off of public funds must also be open access. And that is one step in solving a lot of the issues we have with, the publication industry, the publishing houses and stuff like that we have for academic work. But it's still just a small step in terms of many different things we have to do to make this particular ecosystem more open, more friendly to researchers and non-researchers alike. There's a lot of things that we have to do, and the replication crisis is just one of many issues that we need to solve. It's just that this is one that is particularly it grabs the attention of people who hate academics, and is using conspiracy theories a lot, right? I think this is one of the issues I have with Sabine's science communication, is that yes, she's willing to field these discussion points, and these discussion points are incredibly valuable to have, but they have a lot of nuance to them, right? And if you don't have those discussions with the nuance, and instead you talk about it and you take the side of the conspiracy theorists, saying that the entire system of academia is flawed. Yes, there are flaws, there are cracks, but at this point, it's not broken to the point that we can't fix those cracks, you know? And that's my personal opinion. Let me catch up on chat. I missed a whole bunch. There are efforts like you have to publish result regardless of its positive or negative result. Yeah, this is also another thing. We have to publish negative results as well. That's important to do. Anyway, but the problem is it's very difficult to prove a negative. So like just because your experiment failed does not mean that this particular idea is a failure. It could just mean that you're a failure. You know what I mean? Like you could just be an idiot. I say as someone who's done this multiple times, and it's not very clear as to, you know, whether, this is what I mean. Like, this is why it'd be really nice to have like an open researcher community, like on Twitch or YouTube or something like this, where people can just like kind of pop in and like, imagine if I was not the only researcher on Twitch, and there were a whole bunch of other people doing research on Twitch, and like, you know, I'm tired. I'm like, hey, I'm just going to pop onto, I don't know, this person's stream, and we're going to talk about what he's doing, why, or she's doing, or why it's interesting, all this kind of stuff. Like, then we can have these kind of conversations publicly, and we can kind of suss out whether, like, I'm an idiot for my thing not working, or, you know what I mean? Like, it's easier to suss out this kind of stuff if it's done publicly. And it's been one of my dreams to be able to do research in a public fashion for a long time. I'm not very good at it. But I think most people aren't very good at it. My point is that, like, when it comes to, like, negative results, it's just very hard to publish these results because it's very difficult to know why the study failed. And there's so many different ways it could fail. And so you can't prove anything except that you're an idiot with you know, negative results. So that's why people don't publish them as much. What do we have here? Yeah, we need more money and more power to detect these made up particles. The LHC is now like an economy black hole. Yeah, okay, I'm gonna ask something really stupid here and something I should know. Why do we care about these particles? Like I should know this. I'm a physicist. I have a physics degree. But why do we care? Like, what is the advantage for knowing about these like subatomic particles? I don't know. This is what I want to know. And someone here in chat is going to tell me right now what the purpose is. And I want to know. Tell me. Maybe people think auditing is unproductive. But if there is garbage, it's very productive. Exactly. I mean, we have peer review, but peer review needs to be more strict, right? Or if this is press garbage. The specific idea I'm trying to understand, if true, is how a group of physicists can cheat the system by having a little circle that secures funding by doing ineffective science, while outsiders don't know enough to tell it's bad science. I think that's what Sabine fears may spread to other fields. So this is what I don't know, right? And this is why I'm a little bit hesitant to agree just point blank with what Sabine says. Because yes, there probably are like small fields where like only very specific groups know the area, and I could imagine specifically with like subatomic particles and stuff like this. Look, the math is insane, absolutely insane, to a point that I can't even begin to fathom the mathematics necessary to solve these problems. Right? It's just crazy, absolutely crazy. And so probably it could be entirely possible that this small group of people just kind of made stuff up. And they're constantly taking money from the system. But here's the thing about conspiracy theories, right? The easiest way to tell whether a conspiracy theory is true or false is to determine the number of people that have to keep their mouth shut in order to keep the theory alive, right? So let's take the flat earth theory. So there are billions of people on Earth. Okay, how do we put this? In order for the flat earth theory to be correct, right? I guess it's not a conspiracy theory, but there is this idea that people are keeping the truth from you, right? They're trying to prevent you from learning the truth that the Earth is actually flat, because there's billions of people who are all saying that the world is round. So there has to be some group of information, or some group of people who have the information that the Earth is flat, right? You know, it's one of those things where this one maybe isn't a good example because it has to be like experimentally validated, and it's very easy to experimentally validate that the Earth is round. So let's think of another example. Let's think of like, I don't know, anything with the deep state or something like this, where people are like, oh, you know, these people are trying to prevent the world from learning the truth, right? Just count the number of mouths, count the number of people that would have to keep a secret in order to maintain this lie, right? If it's like 10 people, it's entirely possible that these 10 people all have like a special group, and that they're hiding that from the population of the world. But if it's like 1,000 people, or like, 10,000 people, the entire Department of Energy or something like this, like, now it's becoming unbelievable, right? And so if there is a small group of physicists who are cheating the system and getting funding based on just some crazy result that cannot be replicated in any fashion, how small is that group? Like, is it 10 people, 100 people? Like, at some point, people will be using these results from these papers for other things, and then the lie will be known, because again, you can't build upon a crappy foundation. So once that foundation is found out to be crappy, then what are these people going to do? It's one of those things where it's like, I agree that this is happening, but you argue that it's happening at a scale that is appreciable, or I agree that this thing could be happening, but to agree that it's happening at a scale that it could fundamentally affect science all over is also ignoring the fact that, again, every single person that builds upon their paper must also at some point, redo their experiment in order to show, or go through their theory in order to show that this is correct. You know what I mean? So anyway, I guess what I'm trying to say is, the longer the papers are out, and the more people who are replicating the results in order to build upon their work and to create new papers, the easier it is to find these people. So the correct answer to this small group of people taking funding, I think is just to leave them be. I mean, they certainly can't be taking enough money that is going to like fundamentally change the landscape of science, because it must be a group of like 100 people at most. 100 even sounds too big. It's probably 10, and so that's not a huge number of people, and it's, anyway, I'm not as doom and gloom about it as other people might be. More funding for reproduction and peer review. Yep. There is actually no funding in peer review, just for the record, in case people didn't know. When a paper is peer reviewed, basically nobody gets paid for that review. You're doing it out of the goodness of your heart. Now that, wait, I've got a lot of chat here to catch up on, some chat down here as well. Not that BS where you are peer reviewing for free. Yeah, look, peer reviewing for free obviously sucks, More open, they could just take a page from the IT industry and make meetings over meeting. Yeah, this is the other issue. Yeah, too many meetings. I understand. Make a plan, and whatever you have, you make public every year, or 3 months or 6 months, I don't know, something. When you let people review and reproduce, right? New physics, and the hope that you use that for new things. Yeah, honestly, new physics is the number one way to fix a replication crisis. The more you use the results of studies in order to make new results, the more you test the old results, right? It's I think everyone kind of knows this. Validate fundamental physics theories. It's part of the origin story. I reckon that's what discovering these particles mean. We care to the point that we made sure the theory is correct. Maybe I just don't understand the origin story. Maybe that's what it is. Maybe I don't have a clear enough picture of why people would care, because like, I don't have a clear enough picture of like, what is the origin story? Is this string theory? Is that what it is? Fluoride in drinking water? Dentists would have a pretty good idea. Yeah, people are targeting fluoride in water. There were even people in this chat that were targeting fluoride in water a while ago. I see you guys down there. I'll catch up on that. Give me a second. If you need that kind of, why is that pinned? If you need that kind of machine to detect it, and it has no real impact, immediate measurement, then it won't really affect new things. I mean, I think when we start talking about negative results, one of the biggest negative results that people talk about is the Michelson-Morley experiment. Now, this was an experiment a while ago to determine whether there was this thing called an ether, a thing that allows for light to propagate through, like this goop that we all live in. It was a very interesting experiment. And what it showed was essentially it's very unlikely that some sort of ether exists, where ether is, again, this goop that is ever present amongst everyone. It's like this entity that allows for electromagnetic waves to pulse through, right? This is one of those experiments that really did fundamentally change the landscape of human knowledge, and is very important that everyone knows about. I won't go into the details so much, but when we're talking about like new results and stuff like that, I don't know, I just feel like it's important to mention that, again, these negative results do sometimes appear, and they are very fundamental, right, and very important in certain areas, right? And so as people start putting out bunk theories, if the bunk theory is important enough, someone's going to do another Michelson-Morley experiment. And then when that new experiment comes in and it tests the results of the bunk theory and it realizes that that bunk theory is bunk, that's when like things start to matter, right? Like, how much money did we put into the Michelson-Morley experiment? I don't know. But again, I don't know. It's such a weird argument to have. Like, I don't know the actual answer here. Like, I don't even know what I'm really trying to say. But it's just a small group of people should not affect the larger scientific consensus in my mind. But maybe I'm wrong. I think... Oh, I missed something. I think the argument doesn't have to do with keeping secrets. The papers are public, after all. It has to do, in my understanding, to the normalization of practices. It is true that there's a whole bunch of scientists who are not very good at being scientists, and it's something that we should probably talk about some more. For so long, 67, thanks for following, really appreciate it. They just, if they are successfully kept, otherwise they fail and burn all the data. And as I said, we won't know. Ether. Yeah, Ether. Am I mispronouncing it? It's Ether, right? I missed a lot down here, Hanif. Let me go ahead and catch up. Their efforts, like you see, Insular Journal, it's very unlikely to even be mildly known, let alone listed as a trusted journal. I missed what that was responding to. I'm so sorry. So many journals have been discredited because of conflict of interest, owner publishers, their own papers, etc. If we went to talk about the bad researcher, I'll point out our creationists like James Tour. Even he can't hide his grift for long. James Tour. I went on tour. Wow, I didn't know that. My goodness, this guy's so good at his conspiracy theory that even, I didn't even know I went on a tour. Okay, so let's see, what is it? James Mitchell Tour is an American chemist and nanotechnologist. He is a professor of chemistry, professor of materials science and nanoengineering at Rice University. His name is James Tour. He didn't go on a tour. It isn't the James Tour. His name is just James Tour. All right, fair enough. Received a degree from Syracuse. So what did he do? Opposition to evolution and origin of life studies. Tour became a born-again Christian in his first year at Syracuse and identifies as a Messianic Jew. Tour signed the Scientific Dissent from Darwinism, a statement issued by the Discovery Institute disputing the scientific consensus on evolution. But in spite of the Discovery Institute's promotion of the pseudoscience of intelligent design, Tour does not consider himself to be an intelligent design proponent. According to the New Yorker, Tour said his signing of the dissent reflected only his personal doubts about how random mutation occurs at the molecular level, and that apart from a habit of praying for divine guidance, he feels that religion plays no part in his scientific work. I don't know. There's a whole university only for Rice. Oh, good old Rice University. Man, that would be amazing. To be fair, look, there's a lot of good research in rice. There's like the golden rice or whatever it is that came out recently that has like all the nutrients you need. I don't know. It's pretty cool. Anyway, so story time. I got a PhD from the Okinawa Institute of Science and Technology Graduate University in Okinawa, Japan. That was a mouthful. I say it every time. There was one day in the middle of my PhD, 1 week, I went back to the U.S., right? It was for my sister's college graduation, I believe. Yeah, college graduation. When I was there, I'd been doing the PhD for a while, and I don't know, I'd been enjoying my life as a PhD student. I genuinely loved my time at OIST. I was spending all day reading papers. I was streaming in the morning. I was doing so much stuff. I was doing research during the day. It was great. I loved it. I come back home, and somehow all these people who used to be very friendly to me were very hostile. I didn't understand why, right? And I still don't fully understand why. They started talking to me about how scientists are all atheists and how, they didn't understand that because aren't scientists, discovering, God's work by doing their research. And then they started talking to me about how, evolution is a crazy theory and that it can't possibly exist and how climate change is a hoax. And I'm like, guys, why are we talking about any of this? I'm not, this isn't like a stump the scientist type of situation. I came back. I want to enjoy my time coming back. I don't want to debate someone about evolution. But while we're here, I guess I can tell you what I know about evolution, which is that it fundamentally changed the landscape of biology. Sure, potentially it doesn't necessarily exist in the way that we imagine it to exist. Maybe there's some like other formulation that can also say the same thing, but it works as a tool that allows scientists to classify, different groups of animals and plants, and that's a perfectly worthwhile thing to have in order to make sense of a lot of key stuff. It's like if you came to me tomorrow and told me that quantum physics, the interpretation of quantum physics is different than what we thought, right? And you told me that this changes everything. I mean, in a sense, you're right. The interpretation of quantum mechanics, like let's say we don't use the Copenhagen interpretation, we use some other interpretation. It does matter, but in another sense, it doesn't, right? Because quantum as a tool is exactly that, a tool. We can do quantum engineering. We don't necessarily have to know all the details of the underlying physics. It's okay because we can use it at a particular level. It's like when no one claims that Newtonian physics is wrong, right? That's the physics of like balls dropping and like F equals ma, all this kind of stuff, like the physics you learn in high school. It's not wrong exactly. It works at scale. It's just that when we start talking about very small things or very large things, it ends up breaking down, right? So just because the interpretation of quantum mechanics is maybe slightly different, that's okay, because for the most part, it works. And it doesn't really matter if like some small nuance changes here and there. It's just we know at these scales, quantum works in this way. Maybe as we get really, really small, there's another set of laws that we use to do really, 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 really small stuff. Maybe as we start talking about antiparticles, they also work in a different regime, right? It's okay to have these different patches where we use different formulations for these different patches, We use Newtonian physics for big stuff. We use quantum physics for small stuff. We use relativity for really, really big stuff. It's okay. I don't have a problem with this. I don't think there needs to be this underlying theory that works for everything, It's totally fine to have separate theories for separate groups. Maybe in the future there is some underlying theory. There is a way in order to connect everything. And that's okay. That works too. But, we're 400 years on from Newtonian physics, and yet still people are using it for a huge number of tasks, right? Because it's great, So I don't see in the next 400 years people like just throwing away all the stuff we've done with general relativity or quantum physics or something like that. Maybe in like 1,000 years we'll look back and we'll be like, look at those hobos. Man, they didn't even understand, I don't know, quark drives, whatever it is. We'll look back and at how we are thinking today. In 400 years we'll look back and we'll say, man, those guys clearly didn't understand, anything. It's amazing that they were as, productive as they were, considering they didn't even understand X. You know what I mean? And that's fine, because, we're at the boundary of human knowledge as it is now, and in the future, the boundary is going to change, and we're going to be at that boundary, and then we're going to be at a new boundary, and a new boundary, right? That's just how it is, Speaking of interpretation of quantum mechanics, do you have thoughts on superdeterminism? No, I don't even remember what it is. What is superdeterminism? I have to remember what that is. Is a loophole in Bell's theorem by postulating that all systems being measured are correlated with the choices in which measurements to make them on. Are correlated with the choices of which measurements to make them on. The assumptions of the theorem are no longer fulfilled. Yeah, I don't remember much about this at all. People still argue on how we build pyramids. Look, it's incredibly obvious how we built pyramids too. The fact that anyone is arguing that aliens don't exist, it's insane to me. We know they exist. We have clear evidence that they came in and they built the pyramids, and yet still people are arguing about them. I don't know what we're supposed to do if we can't even agree on basic facts. This is yet again, the liberal media is hiding the truth from us. 1 second, I gotta cough again. Anyway, that was me being stupid. I did have one final thing. I do actually want to start talking about analog quantum computation and stuff like that. This is a point I've been trying to do this, a couple days in a row. I haven't done it yet. So what I want to say is the following. I know for a fact that I'm an idiot. In hindsight, people are going to look back, and if they think of me for even a second, they are going to think of me as an idiot. And that's totally fine. I don't mind being known as an idiot. But at least I'm an idiot who's trying new things. You know what I mean? It's one of those things where, we're going to look back 100 years from now, and we're going to see all the ways in which the world was wrong. We were wrong. We were thinking about the world in wrong ways. You know, and that's okay. It's okay to be wrong. But the fact is, with the knowledge that we have, we can still push and do things that people haven't done before. And I think that's what's important. You know, the other day I wrote a line in my book. It was about failure, and it's about how, like, the one thing that this character can like consistently rely on, like the one thing that, you know, how do I put this? I'm not doing a very good job describing it, but basically the character said that there's one thing that he prides himself in, and it is failure, you know, because it's through failure that you learn and you can improve and you can push and you can do things that you couldn't do before, right? And so, sure, nowadays we have all these theories and all these ideas of how the world works, and that's fine. It's great to keep working on them. But it's not okay to use these theories as ways to discredit clear other practices. You know what I mean? Like, sure, it's great to learn and to think about the like interpretation of quantum, but the fact is we can still use quantum for a lot of things, and it's great for that, you know. And when it comes to like string theory, it's great to study this type of stuff, but we shouldn't be so beholden to it that we end up like ignoring other types of research as well. You know what I mean? Like, I don't know what I'm trying to say, except that like these types of theories end up grabbing people for better or for worse, right? Like, you know, there's going to be a whole bunch of people who are really into string theory because that's where the smartest people on earth go. They all do string theory, right? But that means you're going to get a whole bunch of cranks, and you're getting a whole bunch of people who don't know what they're talking about, who think they know what they're talking about. And it ends up becoming a beacon for both the best and brightest and also the dark and dimmest people in society. You know what I mean? It's just people who want to sound smart will go there, you know? And so this is kind of another reason why I've been staying away from these theories. I don't want to be the guy that discovers the theory of everything. I don't want to be the guy that, you know, like, this is not interesting to me. What's interesting to me is being able to just do my small little puzzles, have those small little puzzles, you know, affect the world in small little ways that hopefully will have a bigger impact down the road. I'm happy to just be one of many people contributing to that boundary of human knowledge. I don't have to be the guy who makes the biggest step, you know? And I think that's kind of what I'm trying to say here. I too am an idiot on my own terms. Smart person learns from his own mistakes. Wise person learns from others. To me, string theory is like solving Collette's conjecture. Yeah, I agree with this. And also, Anakim, I think what I'm trying to say is the following. I'm not very good at describing this thing, but I think, you know, there's a general philosophy I have that you should always be the dumbest person in the room, right? That's my general philosophy. You should always try to be the dumbest person in the room, because the dumbest person is the one who asks the most questions, and also the dumbest person in the room. It means you've set yourself up to be surrounded by smart people, and as long as you're surrounded by smarter people, you're going to be lifted up as well, right? And so, you know, there's a lot of people who like pride themselves on like being able to figure out X, Y, and Z, and that's fine. But for me, I'm more of someone who just likes to, I don't know, I'm talking out of my butt right now, but I'm more of someone who just, you know, likes the process of learning and wants to do that more. And in order to learn the most, you've got to acknowledge that there's stuff that you don't know and go from there. That's, I think, what I'm trying to say. I think in hindsight, you know, if anybody remembers me, like let's say in 100 years, if someone remembers who James Schloss was, you know, I don't think they'd remember me for any scientific discovery I made. Maybe they do, but I don't think they would. If anything, they'd remember me for, I don't know, maybe a book I wrote or something like this. But more than likely, my hope would be they remember me as a guy who is just completely filled with ideas that didn't quite work, but at least he was trying. You know what I mean? There's a whole bunch of scientists that are like this. They keep trying, and something kind of sticks, you know? And that's okay. Like, it's okay to be part of the, like, group of people just trying their best to figure something out. And contributing in small ways, you know. So with all that said, we've been rambling for 2 hours and 30 minutes on top of a discussion that we already had about publishing. So we've talked about publishing novels, we've talked about publishing papers, we've talked about scientific theories of different types. Now let's move on to actually talking about analog quantum computing. And what I'm going to do is I'm going to go to Discord, and I'm going to go to the paper pile. I'm going to go through what we had last time at the end of the last analog quantum computing discussion. And we're going to refresh ourselves about what we were talking about. So let me go here, and let's paste that down there. Okay, so last time, we wanted to have a conversation about analog quantum computing. And we did not have a discussion of analog quantum computing. Instead, we talked We talked about AI and copyright. We talked about GPGPU. We talked about Julia and GPGPU. We talked about pseudoscience. Turns out we're doing a lot of cyclical arguments today as well. We've also talked about a lot of these topics, and not so much AI and copyright, but we talked a lot about pseudoscience. And for the record, I think it's really, really good to have these conversations. So last time, when we did talk about quantum computing, we talked about how it's related to existing tools in Julia, because that's what I know. So we talked about what Julia can do. It can do simulation of quantum mechanics. You have QASM, which is quantum assembly. This is actually something we might want to look into more. We talked about what quantum computing can do that's better than classical computers, which, to be honest, I still don't know if I know the answer to. I'm trying to figure that out. There's a few small-scale examples where quantum computing can win when compared to a quantum computer, but it's not very clear to me as to what those examples are. We then talked about how quantum computing should scale with error correction. We talked about different types of quantum computers, and then we talked about YAO as a Julia package that we might want to go through to learn some more. Okay, so what's the difference between regular analog computing? This is what I don't know. What makes an analog quantum computer analog? I don't know. So we need to look into a little bit more. So what I'm going to do now is, rather than going down the Julia route, trying to figure out what we have in existing tooling for existing languages, I'm just going to Google analog quantum. I'm going to put that on Google Scholar. Okay, digital analog quantum computation, behavior of analog quantum algorithms. Okay, this might be what I want. Let me go to the PDF here, and let's just read this paper. What a great, isn't the quantum analog by nature? Yeah, so I'm going to try to find a couple of good, papers to read so I can get a better grasp on what's meant by an analog quantum computer, right? I don't know what that means. I understand a digital quantum computer uses qubits, right? So what does an analog quantum computer use? But a lot of people think it is continuous signals instead. Yeah, I don't know. I need to learn. Analog quantum algorithms are formed in terms of Hamiltonians rather than unitary gates, and include quantum adiabatic computing, quantum annealing, and the quantum optimization algorithm. There we go. These algorithms are promising candidates for near-term quantum applications, but they often require fine-tuning via the annealing schedule or various parameters. In this work, we explore connections between these analog algorithms, as well as limits in which they become approximations of the optimal procedure. Notably, we explore how the optimal procedure approaches a smooth adiabatic procedure, but with a superimposed oscillatory pattern that can be explained in terms of the interactions between the ground state and the first excited state that affect the coherent error cancellation of diabatic transitions. Gotta be honest, lots of words there. This is a lot of words. This is from 2021, but I think that's okay. I saw the Analog QC headlines the other day and started Googling the same questions. Yeah, I need to learn about this, right? So this is a lot of words that I'm hoping the introduction tells me a lot more about. So let's talk about the words I don't know. So first of all, I don't really know the quantum approximate optimization algorithm. Look, I'm an algorithm guy. I don't know this one. I should know this one. Let me open this up on Zernal PP so we can just start annotating. So we'll do Zernal PP, downloads, and then 2107. Here. Also, just for the record, I need to state this. Notice how I just went to Google Scholar and I just picked a random paper, right? One that just looked good, right? For the most part, this is what I recommend people do when they're trying to break into a field. They pick one that looks like it could answer their question, because the hope is that that paper actually will link to another paper that gives them the real information that they're looking for, like a review article or something like that, right? Because remember, when you enter the scientific literature, you're not looking for one paper to solve your problem. You're looking for an entry point into this rabbit hole that is the field that you want to go into, right? And so just because I picked on a random paper doesn't mean we're going to go through this paper. What I'm doing is I'm trying to read this paper in as much as I can understand where to go from here, right? And that's an important thing when we're reading papers. Remember, it's never really the first entry point that you're studying. You're studying the entire field, right? I just have to say that because there's a lot of people who've asked me questions as to like how you read papers and stuff like that. And that's generally how I feel. Like you enter the literature at some entry point. It just happens this is our entry point now. Man, why can't I see my cursor? Wait, where'd the cursor go? Hello, cursor. All right, whatever. And then you go from there. For some reason, I can't see my cursor right now, so I'm gonna try highlighting. Maybe this helps. Perhaps I don't know quantum well and I'm hazy, but light waves seem analog and photons seem digital. I understand that analogy, and I think that is an okay analogy. it's more, but in this case, we specifically have qubits, and then I think we're talking about the wave function in terms of the wave and the like digital analogy, right? So I think it's qubits versus the wave function, but I'm not entirely sure. So things I don't know. Why is this so hard? Let me change. Can I change the color to blue? Does that work? Maybe that helps me read it a bit more. So quantum approximation algorithm. I don't know about this one, right? That's something I need to learn about. So these algorithms are promising candidates for near-term quantum applications, but they often require fine-tuning via annealing schedule, right? I know a little bit about quantum annealing, but I don't know so much about. I need to learn more about it. I need to remind myself. And what it means by annealing schedule, is this like a scheduler like you'd expect from a type of like computational method? You know, like Dagger is a scheduler, direct acyclic graph type of thing. I don't know. Or variational parameters. So variational parameters, again, I should in principle know what these are, what they mean by this, but I don't know what parameters in specific. So in this work, we explore connections between these analog algorithms as well as limits in which they become approximations of the optimal procedure. Again, what do we mean by optimal procedure? I don't know. Notably, we explore how the optimal procedure approaches a smooth adiabatic procedure. Smooth adiabatic procedure simply means a procedure that allows for us to transition between states without exciting it. So it just means, like, if we have two ground state, or like a ground state and an excited state, an adiabatic passage would be something that is so smooth that you can transition all the particles from one state to another state without overexciting, if I'm remembering correctly. Man, I have to learn a lot. I've forgotten everything. Searching global minima and maxima use some sort of artificial annealing algorithm sometimes. Yeah, I think this is where, so quantum annealing is based on that. So the question is the question is how the relation is. So far we have a lot of words we need to learn. But with a superposed oscillatory pattern that can be explained in terms of the interactions between the ground state and the first excited state. Yep, so I knew it was between ground and first excited. That's fair. I'm going to go ahead and delete that one. That affect coherent error cancellation of diabatic transitions. So that's what I don't know about. So essentially what we're saying here is some sort of adiabatic method. Cancellation of diabatic transition. I've actually never heard of diabatic transitions. They must be the opposite of adiabatic, which adiabatic is like smooth and without exciting anything. The stuff I need to learn. Something about slowly lowering the temperature. Right. That's exactly what we're doing here. Furthermore, we provide numeric and analytical evidence that QAOA, the quantum approximation optimization algorithm, emulates this optimal procedure with the length of each QAOA layer equal to the period of the oscillatory pattern. Additionally, the ratios of the QAOA bangs, are determined by the smooth, non-oscillatory part of the optimal procedure. We provide arguments for these phenomena in terms of the product formula expansion of the optimal procedure. Okay, I'm learning a bit here. With these arguments, we conclude that the different analog algorithms can emulate the optimal protocol under different limits and approximations. Finally, we present a new algorithm for better approximating the optimal protocol using the analytic and numeric insights from the rest of the paper. In practice, numerically, we find that this algorithm outperforms standard QAOA and naive quantum annealing procedures. Okay. Long story short, we have to throw basically everything we're thinking about digital quantum computing out the window. So we're not talking about qubits here. We're literally talking about creating a device that is directly simulating quantum states, okay? And in that case, we can describe everything as a Hamiltonian as a way to describe, the Hamiltonian is a way to describe a system. If you're familiar with classical physics, you might be familiar with the Lagrangian. It's a very similar case. But if you aren't familiar with Lagrangian, don't worry. All the Hamiltonian is a way to describe the energy movement in the system. And so essentially, as long as we can describe our system with a Hamiltonian in a similar way, then by doing analog quantum computation, we can simulate that Hamiltonian. And I guess the hope is that it's a way of simulating a Hamiltonian. So basically any system, any quantum system, it's a way of simulating any quantum system in a systematic way, right? And so the idea would be you have a Hamiltonian and your quantum computer can just simulate that Hamiltonian. This is interesting, completely different than quantum information theory, which is all about qubits and all this kind of stuff. This is basically just saying we're doing quantum simulation with a real physical device that is easy to manipulate. Completely different. So I want to learn a bit more about this. So let me see if we can. So analog quantum algorithms come in a variety of forms. We have adiabatic quantum computation, quantum annealing. Oh, this is great. This is exactly what I need. Lots of references. Variational algorithms such as a quantum approximation optimization algorithm, QAOA. Analog quantum algorithms are particularly relevant in the noisy intermediate scale quantum device. Okay, I don't know about this at all. Era where they are capable of running effectively on small scale devices. So my guess is the following, right? So one core issue with quantum information theory and quantum computing is that as we start scaling these quantum computers, it becomes incredibly difficult to deal with error correction. This is the showing that a quantum bit is actually the correct bit that you wanted out from that bit. Sorry, I just hit the microphone. And so the idea is if we can reframe everything as an analog algorithm instead of a digital algorithm, so an analog quantum algorithm instead of a digital quantum algorithm, in principle, we are able to deal with a noisy intermediate scale quantum device, which would be the scale at which you care about error correction. In principle, this allows us to create systems that don't have as much error, hopefully no error. It's just the error that you would get inherent within the Hamiltonian, the way you're describing the system. And that would be great, right? But it does require you rewriting all the different Hamiltonians. So this already gave me a lot of information. I think what I want to do now is take a second to learn more about adiabatic quantum computing, quantum annealing, QAOA, and noisy intermediate scale quantum devices. So what I'm going to do is I'm going to grab this paper, and I'm going to, I guess, just save it. I don't need, I'm going to move it into a separate folder so we can talk about it later. So let's go ahead and discard this, and we're going to do the following. We're going to cd into projects. You guys can't read this. It's okay. And then we can do ls cd into Simuleos, ls make a directory quantum. I probably already have a quantum, don't I? We'll say analog quantum. All right, cd analog quantum. And we're going to move the file here. 1 second. Downloads. Come on. And then what's the file number? 2107. Here. Okay. So that's paper 1. Instructions unclear, became insulin deficient. Is this because there's too much sugar or not enough sugar? How does that work? Okay. Next thing I want to do is take a look at these references. Also, guys, I gotta go blow my nose. I'll be right back. I'm so sorry. 1 second. Oh my goodness. My goodness. Because adiabatic, that's pretty good. Adiabatic, ha ha. Okay, so let's go ahead and read some papers. Let's first talk about the noisy intermediate scale quantum device. So it's paper 4, quantum computing in the NISQ era and beyond. All right, let's just read this. It's in Quantum, which is actually a well-known journal. It's about the same as, what is it, NJP, New Journal of Physics, which is about the same, a little bit higher than PRA, PhysRev A in terms of like journals that you can publish to. Basically, it's reasonably well respected. All right, let's go over here. Let's go to Google Scholar, and let's see if we can find this paper. Yes, this is what I'm looking for. It's from 2018, cited by 8,568 people. Holy cow, the J. Preskill here. What a paper. Quantumjournal.org. Sure, let's grab that bad boy. Oh, I was expecting a PDF. Full text PDF. Let's go. And we're also going to put this into the same directory. Let's move this over there, and let's go here. Projects, Simuleos, analog quantum, and we're going to move downloads Q dash here, and we're going to do Zernal PP Q dash. Come on, there we go. All right, quantum computing in the NISQ era beyond and beyond. All right. One thing I don't like about quantum, I like the double column layout. I mean, I know I'm being a little bit biased here. I just like double column layout papers. It looks like we have 20 pages here. Let's just read through it. This might be a good paper to get information from. Okay, noisy intermediate scale quantum technology will be available in the near future. Cool. Quantum computers with 50 to 100 qubits may be able to perform tasks which surpass the capabilities of today's classical computers. That I want a little bit of a qualification on. But noise in quantum gates will limit the size of quantum circuits that can be executed reliably. NISQ devices will be useful tools for exploring many-body quantum physics and may have other useful applications, but the 100-qubit quantum computer will not change the world right away. We should regard it as a significant step toward the more powerful quantum technologies of the future. Quantum technology should continue to strive for more accurate quantum gates and eventually fully fault-tolerant quantum computing. This is totally fair. At what point can you stop calling something a computer? If something fizzes in water and dissolves, can you stop saying it's computing something? What do you mean by that? So like, it is a good question though. Like, what constitutes a computer? Like, what is a computer? It is something that computes a value for you. So back in the day, for example, Feynman's day, he was working on the fastest supercomputers that existed at the time. These existed, I think, mostly in Los Alamos, but in several other national lab facilities, as they still do to this day. And his concept of a quantum computer was essentially a tabletop physics lab that was essentially a configurable way in order for you to create a system that reliably solves the Hamiltonian, right? At that time, the definition of a computer was quite different. And in fact, exactly what Chocolate Mints is saying, there was a time when a computer was just known as a room full of usually women performing calculations. And in fact, the original supercomputers, when they were created, the question was, is this computer actually as reliable as this room full of people doing calculations instead? So they would have to actually test the results from what we consider a computer to be. They had to test those results against like man-made calculations to verify their accuracy, right? And so it really does depend on what we call a computer and how we've classically called them computers and all this kind of stuff. So I think we're at the era right now where what we currently consider to be a computer is going to change in the next 50, 100 years. And so I reckon that, let's say quantum technology does take off and all computers are now quantum computers, well, then we don't call them quantum computers anymore. We call them computers, right? And then what happens to classical computation? What is that called now? I don't know, right? I mean, it's just one of those situations where like, I think the definition of a computer changes so drastically depending on who you ask that it's not a relevant term to keep in mind. Maybe the thing the human is using to perform a calculation, I think that's probably a fair argument, right? Is an abacus a computer? But you could also argue, yeah, I mean, it depends on what you want to argue. Like, is the phone a computer? Is it, I mean, because are you actually asking it to do computation or is it just doing the computation in the background? Anyway, it doesn't matter. We're really being quite pedantic here. And I don't think it really matters. The fact is, we'll leave it at a computer is something a human is using to perform a calculation. This could be a classical computing device with classical bits. It could be a quantum computing device, or it could be, the abacus is a computer, a digital computer. Is it a digital computer? No way, right? It would certainly be an analog computer, right? Is abacus a computer? Yeah, I don't know. I'd argue it is. I don't know. It's calculator. I don't know what the difference is. So, what do we want to read about this? I'm going to skim this really quick. And we are going to... Actually, this seems like a really good paper to read. I mean, it's quite simple. I think anyone could probably read this paper. So let's go through and see what it says. So introduction. Oh, everything on. What time is it? It's 2:30. Now is an opportune time for a fruitful discussion among researchers, entrepreneurs, managers, and investors who share an interest in quantum computing. There has been a recent surge of investment by both large public companies and startup companies, a trend that has surprised many quantumists working in academia. A trend that has surprised many quantumists working in academia. Oh my. Imagine going up to some researcher and being like, hey, I want to use your research in a product. They would probably be appalled. They say to themselves, what? No, I thought I was a pure researcher. I don't want to do any of this applied stuff. Step away. I don't want your money. I want to just sit here and publish papers on useless stuff for the rest of my life, you know? Like, this is kind of the vibe I'm getting from this. Is like a trend that has surprised many quantumists working in academia. Okay, sure. While we have long recognized the commercial potential of quantum technology, this ramping up of industry activity has happened sooner and more suddenly than most of us has expected. In this article, I assess the current status, and future potential of quantum computing. Because quantum computing technology is so different from the information technology we use now, we have only a very limited ability to glimpse at its future applications, or to project when these applications will come to fruition. While this uncertainty fuels optimism, our optimism should be tempered with caution. We may feel confident that quantum technology will have a substantial impact on society in the decades ahead, but we cannot be nearly so confident about the commercial potential of quantum technology in the near term, say the next 5 to 10 years. That is the main message I hope to convey. With that, I am sure that vigorous discussion among all of the interested parties can help light the way towards future progress. This is actually pretty good. This is also my opinion. I feel like we're at this state where quantum computing could be good, but we don't know. And I think most people, like, it really does feel like people are putting, the cart before the horse? Isn't that a phrase? Like, people are like investing a lot of money into quantum without the clear understanding of where it will go in the future, right? It is a bit of a problem, right? And it's probably going to consistently be a problem for the next 10, 15 years until either quantum takes off or people feel like they've been majorly misled at the amount of money and funding that's gone into the field, right? So, opportunities at the entanglement frontier. I'm a theoretical physicist with a background in particle physics and cosmology, but for more than 20 years, much of my research effort has been directed towards quantum information science. I'm drawn to this field because I feel we are now in the early stages of exploring a new frontier of the physical sciences, what we might call the complexity frontier or the entanglement frontier. This new frontier, while different than the frontier of particle physics or cosmology, is very fundamental and exciting. Now, for the first time in human history, we are acquiring and perfecting the tools to build and precisely control very complex, highly entangled quantum states of many particles, states so complex that we can't simulate them with our best digital computers or characterize them well using existing theoretical tools. This emerging capability will open the door to new discoveries. This is definitely true. I do question... So John Preskill is based on a keynote address at Quantum Computing for Business, 5th of December, 2017. Okay, fair enough. I mean, very clearly, this is business-oriented, right? Let me just go ahead and skip some of this. It's almost too much of a PR statement for me. Like, I don't want to sit here and say this is a bad paper. I think it actually is quite good, but it's almost too much PR. You know, like, I don't like it when, I'll read a little bit more, but maybe we skim. For physicists like me, what is really exciting about quantum computing is that we have a good reason to believe that a quantum computer would be able to efficiently simulate any process that occurs in nature. Does this even have references? Does this have references? I want to give me a statement there, because I don't agree with that statement. Any process that occurs in nature? Any process. You're going to tell me that a quantum computer will be better at simulating galactic mergers. Maybe it will, but I don't necessarily agree with that statement. I feel like we have to qualify that. We don't think that is not true for classical digital computers, which, as far as we know, can't simulate highly entangled quantum systems. We don't think that's not true for classic. We don't think that's not true. We think that's true. I don't even know what he's trying to say with this statement. Man, why am I just picking apart everything? Why am I picking apart everything that I'm reading here? Like, I just want references, man. With quantum computers, we should be able to probe more deeply into the properties of complex molecules and exotic materials. But even here, I feel like I'm not clear as to what they mean. And also to explore fundamental physics in new ways, for example, by simulating the properties of elementary particles, or the quantum behavior of a black hole, or the evolution of the universe right after the Big Bang. Okay, dude. Stop. Oh, it's too much PR. I'm gonna have to get another paper, guys. This is not good. So here's my claims. Here's the things that I'm frustrated with. So with quantum computers, we should be able to probe more deeply into the properties of complex molecules and exotic materials. That is not what a digital quantum computer is good at. That's what an analog quantum computer is good at. And also to explore fundamental physics in new ways. Qualify that statement. How? What can we actually do in new ways? And simulate the properties of elemental particles or quantum behavior of black hole. How do we simulate elementary particles better if we're fundamentally at the level of a Hamiltonian, which does not necessarily allow us to simulate the elementary particles to begin with? Like, can a qubit actually eke out more information than a classical bit at this particular scale? I don't know. I mean, I don't know, right? Or the quantum behavior like of a black hole. But the quantum behavior of a black hole is like one of these things that we don't even really fully understand, right? Like, okay, look. I'm working myself into a tizzy here. You can't state that this particular device will help us understand the evolution of the universe right after the Big Bang, when we don't even understand what that means, right? Like, I mean, we do, right? We have an understanding, but like, I'm yet at the stage where I feel like a quantum computer will be able to perfectly replicate everything that a classical computer can currently do. That's what I'm trying to say. I really need qualifications for these claims. Now, let me check to see if it has references, because I feel like it doesn't. And I understand this is a PR. I understand this is a PR paper. Okay, there are references. So give me these references up front. You can't just state things like that. I missed something down here, Hanif. I've seen claims analog computers cannot do a Raman zeta function or gamma function. He's not acknowledging any limitations, right? This is, I think, the problem. Like, the first statement up here was like, oh, hey, let's qualify our claims. Let's think about what we mean. Let's not jump on the bandwagon. Here we're jumping on the bandwagon. We're not even acknowledging. We're saying this is the way we're going. This is it. Quantum computing is the future. And I'm like, what, guys. We have every reason to believe that quantum computation will be good for a select subset of problems. But we don't have the evidence yet to support the claim that it will flat out replace classical computation, right? This is the thing that's bothering me. Perhaps if gravity has quantum elements in it, we can simulate dark matter better. This is the other thing, like, we don't... I need to learn more about dark matter. In my mind, dark matter is literally just a way to make the math work out when we're talking about n-body simulations. I might be wrong, but this to me is where it came from. And when people start arguing that dark matter is like a physical thing that exists, that's when I'm lost. Is it actually a physical thing? I thought it was literally just a way to make the math work out, because we're missing some math when it comes to like the way in which, stars move around in space. Like, it wasn't clear to me that dark matter is itself an object as opposed to a thing that we don't fully understand theoretically. You know what I mean? Wish they combined chats loading YouTube. Sorry. I thought digital quantum is able to simulate chemistry. Maybe analog is cheaper for annealing problems. So my understanding was that digital quantum was not able to simulate chemistry, but that was purely analytical, purely the analog quantum that was able to do that. Because how does a qubit simulate chemistry? At the qubit level, does it understand? This is me guys, remember, I'm learning this for the first time, not for the first time, but I'm learning this again with you guys here. So the amount of knowledge I have in this area is not as much as other people, right? And so if I say something that's wrong, just correct me, but there was a paper that someone sent me a while ago related to the simulation of chemistry on quantum computation. I think maybe I need to go through that paper, because maybe this is what I'm not understanding. Let me see if I can find that paper. It's probably in my downloads somewhere. So let me go to my downloads. Oh, guys, this might not be a good idea. All right, CD downloads, lsstar.pdf. Is there any way I'm going to be able to find this? I have tech suits for officials. Man, I really should not have just like... I mean, now you guys know what I download, right? Why did I think this is a good idea? Oh, this is probably really embarrassing. Oh, it's going to be one of these too. All right, let's see if I can just Google it. All right, using quantum computers to simulate molecules. All right, quantum computation and quantum simulation with ultra-cold molecules. Yeah, no, this is... So if you're saying quantum computation and quantum simulation with ultra-cold molecules, you're not talking about a digital quantum computer. You're talking about a... this would definitely be an analog quantum computer, I would say. Because... See, quantum computation is different than quantum simulation. These are two different things. Quantum computation is using qubits to perform some sort of regular computing task. Quantum simulation is the ability to use a quantum device to simulate an existing quantum thing, right? So it's like obviously ultra cold atoms can simulate a molecule because they're essentially molecules. Like you're able to do the simulation a bit better. Okay. I need to find this paper. How exactly do quantum computers simulate molecular? This might be what I'm looking for. Particle interaction is better than classical computers. Maybe I just read this. Maybe this is what I want. Let's make this bigger. Hello, big. No, Reddit. No, I don't want this. I want this. This is what I want. Get rid of that stupid sidebar, bud. No. I don't want the sidebar. Nah, whatever. All right, I'm gonna try and make it so you guys can actually read it though. No, why do you make the sidebar bigger, man? All right, you guys can probably read it here. So first I'd like to demystify something. It's common that people say an n-bit quantum computer can simultaneously exist in a superposition of two n states, such that it will be able to access two n answers. Thus much faster than classical computers. I already know that's false. You can only get one answer from the superposition of two n states. One measurement will disrupt the whole system, so that the superposition is broken. So an n-bit quantum computer has nothing to do with running two n calculations at the same time. This is true. So just for the record, so everyone's keeping in mind what's happening here. So one of the advantages of using a qubit versus a classical bit is that a qubit has access to a whole bunch of like quantum specific things. And one of those quantum specific things is entanglement. Now what entanglement is the ability to mix different states so that if you measure one state to be, let's say, up, then another spin has to be up. Right? Basically what it's doing is it's saying that, okay, if you measure this bit to be 0, the other bit must also be 1 or 0 or whatever it's entangled to be, right? However you've combined these information by revealing some information on one side of your quantum device, you've revealed information on the other side as well, right? And so what this statement is saying is like, okay, first of all, let's say you do have a quantum computer and you've entangled all these bits together. You're not doing, 2n computation like that. What you're doing is you're performing one bit of computation that has 2n complexity, which is a completely different thing. I wonder if there's a way of knowing the computation complexity of an algorithm through a quantum computing with a quantum algorithm. There is, it's quantum complexity analysis. It's definitely a thing that people do. Okay, so let's go from here. So this is the thing that I'm afraid people are muddling, and I want to learn about what they're talking about. So a TLDR answer would be, because we can construct certain quantum systems so that some physical properties of that system happen to be the same as some formula we need. Yeah, so we can find the Hamiltonian. That's analog quantum computation. That's what it is, as opposed to qubit-based digital quantum computation. You can use this exact same explanation to answer, how do classical computers calculate addition faster than humans? An adder, built with classical electronic circuits like this one, are just some physical objects that do experiments so that if you flip the switches as your input, the output light bulbs will almost instantaneously illuminate in a way that happens to be the same as how addition works. We then measure the on-off of the light bulbs and say that this computer, which consisted of two switches, logical gates, and two light bulbs, can do addition as fast as the electricity can flow through the wire, like billions of times a second. Sure. Yeah, certainly look it up. It's interesting stuff. Okay, so we can now put our switch gate light bulb thing in a case and call that thing a classical computer that can quickly calculate the sum of two 1-bit numbers. The switches are input and the brightness of the light bulbs are output. So what's a fast computer? It's a physical apparatus which we have configurations to change as input. And the measurement of some physical property happens to correlate with some formula we need. Now the same thing happens for quantum computers. I'll use the calculation of a permanent matrix as an example. A permanent of an n by n matrix is a sum of products. Each product is consisted by n elements. The horizontal indices are 1 to n, and the vertical indices are each of the possible permutations for n matrices. Let me see if this gives me more information. That didn't. No thanks. Okay, I think I'm missing parentheses there. So the total number of products in the summation is a factorial of n for 2 times 2 matrices, 3 by 3 matrices. And I generated the permanent for 4 by 4 and 5 by 5 matrices. See what this is? Sure. Okay, essentially it's just a list of permutations of the matrix. That's okay. You can see as the matrix grows bigger, it will be exponentially more complicated as we calculate the multiplications one by one. For a 100 by 100 matrix, you would need to do roughly 10 to the 32 times calculations to get the result. And that will need roughly 1,000 years on our best classical computers. However, there happens to be a quantum process called boson sampling, whose physical properties happen to satisfy this. So we can calculate s factorial 1, s factorial 2, all this kind of stuff, part very quickly using a classical computer. So we now build a quantum apparatus and measure the boson sampling term for a single input. We can now get the permanent of a matrix very quickly from the above equation. And we finally put that apparatus in a case and call the quantum apparatus a quantum computer that can calculate the permanent of a matrix, just like our switch gate light bulb thing. Let me take a look at this. This is a paper. Please give me a paper. No, please give me a paper. Don't give me this. This doesn't give me any information. I want a paper. Give me papers, man. This is what I want. All right, that's fine. That's fine. But tell me what I'm still not understanding. And this is me being an idiot, and I understand I'm an idiot, is at this point, we're literally just talking analog, right? We're not talking digital. Because what he's done is he's created an analog, an analogy to another existing system. So boson sampling is a restricted model of a non-universal quantum computation introduced by Scott Aaronson and Alex Arkhipov after the original work of I don't care about these guys' names, that explored possible usage of boson scattering to evaluate expectation values of permanence of matrices. The model consists of sampling from the probability distribution of identical bosons scattered by a linear interferometer. Although the problem is well defined for any bosonic particles, its photonic version is currently considered as the most promising platform for scalable implementation of boson sampling device, which makes it a non-universal approach to the linear optical quantum computing. Take a look at this. Moreover, while not universal, the boson sampling scheme is strongly believed to implement quantum computing tasks which are hard to implement with classical computers by using far fewer physical resources than a linear optical quantum computing setup. All right, so here's my vague understanding as to what's happening. We have a paper at home. Paper at home is a JPEG. Yeah. That would suck, man. Imagine if all papers were suddenly saved as JPEG. Anyway, what was I going to say? So here's my vague understanding, right? So we have this concept that is a digital quantum computer that uses qubits. And then we have several quantum simulators, which are quantum setups specifically meant to simulate specific things, right? So if you can rephrase your question in the form of a Hamiltonian and solve that Hamiltonian, then you can use quantum to solve that Hamiltonian faster than you can solve a classical problem. You know what I'm trying to say? So the idea is that the quantum landscape in the future is not so much going to be we have a quantum computer, we use it for everything. Rather, we have a bunch of different potential makeups for a quantum computer, all of which can solve very specific problems faster than their classical counterpart, right? Which sounds to me like a different goal than the quantum bit goal, right? The qubit goal is that we just basically allow qubits to do every computation we want. Whereas these guys, I think, are more or less arguing that another solution would be that we have these problems that we know are slow in classical computers. Let's use a specific device to solve those specific problems, right? And if the problem is important enough, then we get specific quantum hardware to do that thing, right? I think this is the future that I'm imagining here, which is quite different than just quantum computers are going to replace everything. Technically, the statement quantum computers are going to replace everything could be correct, but unfortunately, they would be different quantum setups every time. You grind through step by step in digital, and analog bang, there's one step. Right, exactly. This is what I'm imagining as well. And this is why I was relating this to an FPGA, right? Because in my mind, the difficulty here is in physically maneuvering in the FPGA, the way the transistors are like connected or whatever. But in this system, it's like more or less like, how do you configure the hardware to solve the Hamiltonian you're looking for? I think is what we're looking for. Yo, what's up, Communist Schmiegel? But yeah, try to stay based in actual results. So, right. So again, this is one core problem when you're looking into like areas of research that are heavily dominated by popular science articles is that it becomes increasingly difficult to figure out how to cut through all of the just nonsense. Like the paper we just saw, we were just looking at, I think this one. I mean, this is such a PR article. It's crazy. It's crazy that it has 8,000 citations. People thought this was worth citing. I'm wrong. I know I'm wrong. I'm 100% wrong. Look, I need to stop looking at this as a this is a good scientific result, but instead as literally this is just a paper that is covering the basics for people who don't know the basics. It acts as a review article, and that's fine to act as a review article. It's fine. We need review articles. We need papers like this because these are the ones that are readable by anybody. I could give this paper to you right now, anybody watching, and you could understand this, and that's good. That's why I'm a bit skeptical on annealing-based quantum computing. It has its uses, but not as powerful as full fat quantum computing, right? But this is the thing, like when you say quantum computing, you could mean either, and it's not very clear as to what you mean. So I guess what I'm looking at next, let me go back to the previous paper and let's look at another one of those terms. So we're going to go to Zernal PP, and I want to look at 2107. And so we looked at the NISQ, Noisy Intermediate Scale Quantum Device. This is just for the record to keep everyone up to date. What we were talking about there is how scaling quantum computers is quite difficult, right? And we already know that as we start going to this intermediate scale of quantum device, like with, let's say, of the order of 100 qubits, we're going to have so much error on all of our computation that we need to find a way to correct that error. We need to find things that are not going to be as noisy, and find ways in order to mitigate that error. One way is to do quantum error correction, which is a huge field a lot of people are really into. Another thing, though, is to start focusing on more of these analog quantum devices, which have less error inherent in them. Now, keep in mind, I've been talking a lot about these papers that I have not fully read, right? I've literally just gone to the introduction here and a little bit of that other paper, right? And so there's probably a lot of these papers that I need to go through and learn more about. But just, I feel like one of the important things about this stream is just the feeling of getting lost in academic literature. For me, it's quite enjoyable. I really like flipping back and forth between these papers and trying to learn one thing after another and figuring out my own path to understanding something. And this is part of the joy of doing research to begin with. It's just the act of discovering things one step at a time. So we're slowly getting there, right? One day, might not be today, but at some point we will get to where we'll understand what we're talking about here, like what is supposed to be meant or what's supposed to be understood when people say analog versus digital quantum computation, right? What about more resistant qubit, like topological qubit? This is something I want to learn more about topological quantum computing. Well, what is topological quantum computing? What is it? I hear about it all the time, but what is it? What is topological quantum computing? Is a theoretical type of quantum computer proposed by a Russian-American physicist. Sure, it utilizes quasi-particles known as anyons in two-dimensional systems. These anyons, world lines, intertwine to form braids in a three-dimensional space-time. Whew. These braids act as the logical gates of the computer. The primary advantage of using quantum braids over trapped quantum particles is enhanced stability. While small cumulative perturbations can cause quantum states to decohere and introduce errors in traditional quantum computations, such perturbations do not alter the topological properties of the braids. Is there a experimental device here? Is this something that we could make? Experimental efforts. In 2018, Leo, last name, working for Microsoft, published a paper in Nature indicating to have found firm evidence of zero bias peaks, indicating Majorana quasi-particles. In 2020, the paper got editorial note of concern. In 2021, in a follow-up paper, it was indicated that the data in the 2008 paper was incomplete or misrepresented the results. In 2023, Microsoft quantum researchers published a paper in the Physical Review that described a new device that can represent a logical qubit with hardware stability, measuring a phase of matter consistent with the observation of topological superconductivity and Majorana zero modes. The scientists reported that such devices have demonstrated low enough disorder to pass the topological gap protocol, proving the technology is viable. This paper has been criticized by other scientists for not providing sufficient evidence for Majorana modes in previous papers. What's Majorana again? I forgot what this means. What is a Majorana particle? Majorana. Am I even pronouncing it correctly? But the conclusion remains contested. 2018 scientists again claimed to have isolated the required Majorana particles. What are these? One of the cases of interest in Majorana bound states is that they could be used in quantum error correcting codes. This process is done by creating so-called twist defects in codes, such as the toric code, which carry unpaired Majorana modes. The Majoranas are then braided by being physically moved around each other in 2D sheets or networks of nanowires. This braiding process forms a projective representation of the braid group. Such realization of Majoranas would allow them to be used to store and process quantum information with quantum computation. So what topological properties are actually preserved in this? I don't know. Its own antiparticle. I see. So, so what you're saying is it's going to take me a long time to understand this. That's what I'm hearing from this. Man, in my undergraduate university, I had the pleasure of learning electricity and magnetism and also thermodynamics from a professor who was part of the Alpha group. The Alpha group was the group that discovered the first antiparticle, not the first antiparticle, but was able to trap an antiparticle for a particular amount of time. I don't really remember. Was it an antiproton? I don't remember. Anyway, that is all I know about antiparticles. I know nothing more. In a sense, I kind of wish I knew more because it's cool that I worked with someone who worked in that group, or I learned from someone from that group. But I don't know anything. One of my friends actually was like, he was an undergraduate at the time and did enough research to actually be on that paper, and it was a Nature paper. So he got like a Nature publication when he was like a undergraduate sophomore. Incredible, like crazy. No one gets a Nature paper in their entire career, and to get one as a sophomore is insane. But anyway, that's rambling. I need to learn a lot about antiparticles to figure out, to learn more about this particular state. This is one of those things where, like I asked earlier, who cares about the standard model of particle physics? I didn't ask that exactly, but like I don't understand what the utility is, and maybe this is the utility. Maybe this is where we see its use. And this again goes back to why fundamental research is so important. Like, even though I don't understand it, I don't know why we care about this. It doesn't really matter because I'm just an idiot, right? What matters is that people are pushing, and as you start pushing, you eventually start to connect these ideas, and the connections allow for more research. Sorry if you've talked about this topic to death, but what do you think of changes AI language models is making in your field of academic writing? Have you noticed much influence from them yet? That's a good question, and no. I mean, like, here's the truth. Okay. Have people been using AI to write papers? I'm sure there are a whole bunch of people who are using AI to make their writing better. As someone who has met a lot of non-native English speakers, I can tell you probably the output from ChatGPT is maybe a bit better than what they would have written to begin with. Do I agree with this? No, I don't think they should be using ChatGPT for something that they are claiming copyright over. I also acknowledge that they are not truly, how do I put this? The question is either should they write bad English or should ChatGPT write the bad English? And I guess, sure, maybe ChatGPT should write the bad English. Okay, so that's step one. Step two, are they using AI for actual good research? The answer is yes. Not large language models as much, because honestly, those are more or less useless. But they're using AI to do a lot of things, like, for example, computer vision in a lot of different areas for experimental research. Look, AI has been used so much in so many different fields that it's one of those things where, like, yes, people have definitely been using AI for a whole bunch of different things. Now, let's talk about ChatGPT. Let's talk about the large language models, and let's define what my field is. So I do GPU computing, right? It would be wrong for me to claim that AI has not impacted me, because one of the main reasons these GPUs have been selling recently is because CUDA is very popular, and CUDA is very popular because it trains AI. And because of this, my field has seen an explosion in recent years. So simply by nature of existing next to AI, my field has changed dramatically. Now, have I seen large language models actually making a significant impact in any area of research to note? Not exactly. Like, there are certain areas where it's quite useful, right? But for the most part, people are just trying to figure out what they can use it for, right? Like, we're at the stage where, like, we finally have the technology and people are like, oh, well, maybe we could use it for this. Maybe we could use it for this. And I'm sure there's some people using it in, like, the code that they're writing and stuff like this. I would argue illegally. But it's fine. Eventually it will be legal, and maybe it's fine in the next 10 years, you know? So I don't know what I'm looking for exactly. But it's very hard. It would be very difficult, I would say, to have an AI do the work of a researcher. There will be certain places where AI is probably more beneficial, like for example, when you're doing like pattern recognition stuff and all of this. But basically everything that's output also has to be verified, and that verification can take an incredibly long time. I mean, at the end of the day, an AI is not going to be doing the experiment, right? Like, it might be part of the experiment. It might be, you know, part of the thing that is looking, how do I put it? It could be the thing that like, how do I put it? It could be the thing that's like analyzing some data or something like this, but it's not, it'd be very difficult to replace a researcher, right? Because researchers are doing fundamentally different things that have not been done before, and AI fundamentally cannot do things that has not been done before, at least not to the same extent. There is one sub game I play. Some of the people in that high score list just happen to be on the sub that went a long way. Wait, what are we talking about? I'm kind of wondering when they hit a wall based on power consumption or heat management or whatever. Wait, what are we talking about? What sub game are we talking about? What is a sub game? On the sub that went a long way. What is sub in this case? Like a submarine sandwich. Sub game. Okay, so do you guys want to talk? I'm happy to have like a brief conversation about AI and copyright if anybody wants to talk about that really quick. As to why I've been saying that it's not legal to use AI for like any output or anything. This is something that comes up a lot, so I might actually even just clip it and put it into a YouTube short. You're seeing it wrong. You make the job of researcher easier with AI, then you need to pay less researchers profit money. I mean, with the amount they're already paying researchers, they're basically not paying them. Researchers are so cheap. It's probably more expensive to use the AI than to pay for a researcher. Like, I mean, for the most part, they're getting like minimum wage, if that even. It's more expensive to ask ChatGPT, you know? So I don't know. I think you're just, I don't know. Yeah, I don't know. I think there will be a time when ChatGPT is better than it is now. Right now, it's hard to see its use in basically any. It's very difficult to see people using ChatGPT for anything real now. You see it all the time for like internet posts and things like that, but right now, because of the copyright issue, it's fundamentally unusable for most applications. But apparently the topological properties preserved in the topological quantum computing thing was related to spaces whose fundamental group is a braid group. Yeah, this is what I did. Sorry, I didn't understand. I don't really understand what it means when we're talking about these braid groups. It used to be I did. There was a time way back in the day when I was very interested in like knotted stuff, and we were talking about like there's this paper, it was like untangling, I don't know, this stuff like this. Anyway, it's one of those things where I don't remember as much about it, you know? I suck at algebraic topology. Interesting application is in call centers and differentiating types of calls automatically. We need to go deeper. Are you learning this for the first time, or are you brushing up? I mean, look, for the record, standard model stuff, I should know about it because in principle, I learned about it, you know, sophomore year in undergraduate. In practice, I've completely forgotten all of it. I really remember none of it. And so it's a mix between brushing up, but also it's not really related to the stuff that we're doing today. And I don't intend to dive into it much deeper. I was just asking about it because we had a question about topological quantum computing, and I just didn't remember what it was or how it works. And I still don't know what it is or how it works. So, you know, we'll get there eventually, not today. Yes. Okay. So let's keep going. Permanent linear optical engineering, blah, blah. NISQ era. I'm just deleting some tabs here. Replication crisis. We went through some topics today, didn't we? Okay, let's keep going. We're back to the Google page. All right. So we've got a couple other things I want to look at. So adiabatic quantum computing is one. I want to look at quantum annealing. And also the quantum approximate optimization algorithm. So let's look up QAOA first. Quantum optimization algorithms. And I also want to look up quantum annealing. And what's the other one? The last one was adiabatic quantum computing. Adiabatic quantum computation, quantum annealing, quantum optimization algorithm. Okay, let's see what we got here. We'll go through adiabatic quantum computation first. It's a form of quantum computation which relies on the adiabatic theorem to perform calculations and is closely related to quantum annealing. So, first, a potentially complicated Hamiltonian is found whose ground state describes the solution to the problem of interest. Next, a system with a simple Hamiltonian is prepared and initialized to the ground state. Finally, the simple Hamiltonian is adiabatically evolved into the desired complicated Hamiltonian. I see. By the adiabatic theorem. The system remains in the ground state, so at the end, the state of the system describes the solution to the problem. Adiabatic quantum computing has been shown to be polynomially equivalent to conventional quantum computing in the circuit model. Now, adiabatic is slow. So is this why people care about shortcuts to adiabaticity? So shortcuts to adiabaticity are ways in which you can speed up the process by which you adiabatically transfer from one state to another. Okay, that's what it is. Leos, I was in a chat and they were talking about vectors, and something occurred to me that you cannot represent them with one. You can represent them with one number instead of two, like x, y. You use the angle and the number of rotations to represent the length. So 720 would be 2.0202 rotations since its length 2. Is this some sort of mathematical discovery with any significance? So 720 would be 2, 0. I'm not entirely sure what you mean. I think this only works if you know the length. So usually if you have x and y, you can describe a vector with x and y, but you can also describe a vector with like angle and length, right? So you almost always need two values. I'd be surprised if you could embed both values into like a single variable and have them related to each other. But I still don't think there's a way to describe a vector with just one value. You need the two. Are you trying to come up with are you trying to come up with a topological quantum computer still? No, I'm not. I'm learning. Okay, so adiabatic. So a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough, and if there is a gap between the eigenvalue and the rest of the Hamiltonian spectrum. So essentially, what we're talking about here is the transition from one Hamiltonian to another Hamiltonian that happens slowly enough that these transformations can occur. So I need to remember how this works exactly. But I know there was a paper I put out a while ago for basically, it's like particles on a ring is essentially what it is. And these particles have like different behaviors based on like their rotational states. And so you can like basically couple like basically rotation one direction and like different rotational states of like one speed and another speed, right? Oh gosh, I can't remember exactly how this works. This paper was like the first paper I published, so it's a long time ago. But we used the adiabatic theorem there to ensure that we could get to the superposition states. I need to remember more about this. Natural numbers with any arity can be represented with just one natural number. Oh, that's fair. So let's see. So this is important. What it means is that like essentially the adiabatic quantum computation is essentially a way for us to get to a Hamiltonian. Again, a Hamiltonian is a description of a system. And so essentially we start with some simple Hamiltonian, we transform it into a complicated Hamiltonian via the adiabatic theorem. What this means is this happens naturally quite slowly. I don't know what slow means, if that's like on the order of microseconds or on the order of minutes. But there are ways to speed that up with either optimal control or shortcuts to adiabaticity. These are important. Good. So, by the adiabatic theorem, the system remains in the ground state. Adiabatic quantum computing has been shown to be polynomially equivalent to conventional quantum computing and circuit model. So what else do we need here? Adiabatic quantum computation in satisfiability problems. Comparison, D-Wave quantum processors. So the D-Wave 1 is a device made by Canadian company D-Wave Systems, which claims that it uses quantum annealing to solve optimization problems. On the 25th of May 2011, Lockheed Martin purchased a D-Wave 1 for about $10 million. In May 2013, Google purchased a 512 qubit D-Wave 2. The question of whether the D-Wave processors offer a real speedup over classical processor is still unanswered. Tests performed by researchers at Quantum Artificial Intelligence Lab and Google show that as of 2015, there's no evidence of a quantum advantage. Where's the qubit here? So what defines a qubit in this case? Universality results in the adiabatic model. So QMA hardness results are known for physically realistic lattice models of qubits. Yeah, but what defines a qubit in this model? Like, am I dumb here? Like, I thought this is a fundamentally different model than the one with a qubit in it. In practice, there are problems during computation as a Hamiltonian is gradually changed. The interesting parts, quantum behavior as opposed to classical, occur when multiple qubits are close to a tipping point. It is exactly at a point when the ground state gets very close to the first energy state. Adding a slight amount of energy could take the system out of the ground state and ruin the calculation. Trying to perform the calculation more quickly, increases the external energy. Scaling the number of qubits makes the energy gap at the tipping points much smaller. Let's see. It'd be fun to have a guest on the stream you could talk to that knows about adiabatic quantum computation, right? Wikipedia probably is not in depth enough. That's probably fair. Number of dimension, number of qubits. Is that what it is? Number of dimensions of the Hamiltonian? Could be. Yeah, I've considered having guests on and doing like a how do I put this? Doing like a podcast type of thing, but I ended up, I don't know. It's a different vibe, and I wasn't sure if we necessarily want to go for that vibe. So quantum annealing is an optimization process for finding the global minimum of a given objective function over a given set of candidate solutions by a process using quantum fluctuations. Quantum annealing is used mainly for problems where the search space is discrete, so combinatorial optimization problems with many local minima, such as finding the ground state of a spin glass or solving the traveling salesman problem. The term quantum annealing was first proposed in 1988 by B. Apollini. Sure, it was formulated in its present form by these guys through an imaginary time variant without quantum coherence. Though an imaginary time variant without quantum coherence can be discussed by these guys. Okay, sure. Imaginary time is one of those things that people do all the time in quantum. Like imaginary time simulations are essentially ways for you to find the ground state of a system. Purely, like it's not a real entity. It's something that people are using to just simulate and get to the ground state. I used to do it all the time. In fact, most of my PhD was doing imaginary time evolution. Okay, so quantum annealing starts from a quantum mechanical superposition of all possible states with equal weights. Then the system evolves following the time-dependent Schrödinger equation, a natural quantum mechanical evolution of physical systems. The amplitudes of all candidate states keep changing, realizing a quantum parallelism according to the time-dependent strength of the transverse field, which causes quantum tunneling between states, or essentially tunneling through peaks. Okay, good thing we solved the traveling salesman problem now that we shop online. Yeah. That's exactly what we've done with Amazon. It's already done. We don't have to worry about it. If the rate of change of the transverse field is slow enough, the system stays close to the ground state of the instantaneous Hamiltonian. If the rate of change of the transverse field is accelerated, the system may leave the ground state temporarily, but produce a higher likelihood of concluding in the ground state of the final problem Hamiltonian, i.e. diabatic quantum computation. The transverse field, I'm already lost. The transverse field is finally switched off, and the system is expected to have reached the ground state of the classical Ising model. Your paper's boy really sold out in his latest... Wait, Leos, your paper's my boy. Leos, your paper's boy really sold out in the latest YouTube. Did what? What do you mean? What paper boy am I talking about? Pairing function, more general though. We also have Gödel numbering. Let's take a look. Oh, you're talking about the CAS game stuff. An experimental demonstration of the success of quantum annealing for random magnets was reported immediately after the initial theoretical proposal. Quantum annealing has also been proven to provide a fast Grover oracle of the square root speed up in solving many NP complete problems. The 2-minute papers. To be honest, 2-minute papers has kind of sold out a while ago. But what's the latest paper? 2-minute papers YouTube. I don't even know if I'm subscribed to them anymore. I might not be. Unreal Engine 5.5, it gets more incredible. Look, I'm not subscribed to them anymore because like a few years ago, just every single one of their videos was about AI, and I don't care about AI, to be honest. It's not an interesting thing for me to study or research or do anything with. And so sure, it can do interesting things, and I'm interested to see what interesting things it can do sometimes, but it's such a small part of like the overall, like it has not impacted like the papers I'm reading too much, except that I get really annoyed when a paper mentions that they were using an AI for this thing. Like that's really the only thing that's changed for me, right? And so it's not really, I don't know. It's one of those things that just catches attention, but ends up being like really not useful. I don't know how to put it. And so if your entire, like the entire catalog is now AI, and it's just not, it's not enjoyable, you know. It's like I don't want to hear about AI. I'm done, you know. AI. What is RTM here? I used to like his video on computer graphics and fluid simulations. Exactly, right. And then at some point it becomes about AI, and now I'm like I don't care about the AI though. I just don't. It's, you had such good papers, like such good videos out a long time ago. Let's go to the oldest videos here, right? Separable surface scattering, unofficial talk by this guy. Look. These are great. Volumetric path tracing. A parallelogenetic algorithm for Roger's, Roger Elsing's Evo-Lisa problem, right? Real-time control and stopping of fluids. Here we look, these are great, you know? And these are all his stuff, you know? And then we go further, and we have all these like really, really good discussions of these different papers and stuff like that. But you know, the fact is, even at this stage, he's already talking about neural networks and stuff like that. Like, it just, I don't know. Very clearly, when he started talking about AI, the videos became really, really popular. And it's hard to get off the AI bandwagon once you're on it, you know. Okay, quantum mechanics and analogy and advantage. Comparison to simulated annealing. So quantum annealing can be compared to simulated annealing, whose temperature parameter plays a similar role to quantum annealing's tunneling field strength. In simulated annealing, the temperature determines the probability of moving a state of higher energy from a single current state. In quantum annealing, the strength of a transverse field determines the quantum mechanical probability to change the amplitude of all states in parallel. Okay, analytical and numerical evidence suggests that quantum annealing outperforms simulated annealing under certain conditions for a fully solvable model of quantum annealing to an arbitrary target Hamiltonian. So let me take a step back. Here. The reason I'm so interested in analog quantum computation right now is because I have a meeting coming up. A meeting with the CEO of someone who is currently running a company that does analog quantum computation. And as someone who has a PhD in quantum and vaguely knows about machine learning, and I do GPU stuff, and I feel like I'm just kind of right at the door of just actually having a real conversation with this person. And so I want to make sure that like I can ask questions that are not stupid. And I think I know enough now to ask non-stupid questions, but it still won't be like I'm not an expert here, and I think they think I'm an expert. I just need to be very clear with them and saying I'm not an expert. My wife is an expert. I'm not. But I just want to make sure I'm not like, you know, doing something stupid is all. Let me go ahead and learn a little bit more here, and then we might call it for the day. We've been streaming for 3.5 hours at this point, and it might be a good time to go ahead and close for today's stream. Is it a job interview? It's not a job interview. I just happen to be meeting this person. It's completely, I don't know how or why, just through connections that I met in Barcelona, they were interesting. Is anyone really an expert in this field? I mean, look, there are experts in this field, right? It's just a question as to whether these experts are trying to lie to you or not. Advice I hear is to show interest. Probably good anyway. No. Look, I'm not I'm not. This is not a job interview, and I know how to talk to people. You know. Thanks for this. The stream is super interesting. Yeah, I'm glad you guys are here. So let me kind of wrap up some stuff that we talked about today. So, on the Twitch stream, we started today off by discussing publishing. Actually, we talked about traditional versus self-publishing for novels. This was done a while ago, and there's actually a YouTube video right now, or a YouTube VOD of that stream up on my Leos Labs channel. I then closed that stream and I started up a new one where we talked about analog quantum computing. For this stream, we did talk about analog quantum computing, but I still don't know if I fully understand it. Rather, what we ended up talking about mostly was science communication and dealing with people who have different opinions as to how academia is run and why it is run that way. We also talked a lot about, a lot of the buzz around quantum spaces and stuff like that, but we're still missing like a core understanding of what a quantum analog computer is versus a quantum digital computer. I still think, if I understand correctly, the core difference is in the way in which they do qubits. But I'm in that a analog quantum computer is literally just you have a Hamiltonian, which is a way to describe a system, and you're trying to simulate the system. Whereas a digital quantum computer specifically has qubits. But here, the D-Wave does have qubits, right? And so now I'm a little bit confused as to, I'm just a little bit confused as to what that means, you know? Yeah, so I think what I'm going to do is I'm going to close it here because I'm getting a little bit frazzled. I'm a little bit tired. So if you guys have any like questions, comments, concerns, ideas, anything like that, feel free to let me know. Whether here on the YouTube and Twitch chat or over on Discord. Let me go ahead and give you guys a Discord link. Go ahead, create the invite, copy here, paste, and then paste here. Also, if you guys are on YouTube right now, feel free to go down to the YouTube comment section and just leave some notes, right? And maybe digital has a converter, analog shouldn't need a converter. Yeah, I have some stuff I need to learn about, and maybe I know enough to have this conversation with the CEO next week or whenever it happens. That's fine. I think I need to take a step back from the analog quantum stuff and do stuff that I know more about. So tomorrow, I should be live. I think I might do what I said earlier, and I might do a writing stream in the morning and then transition into a science stream in the afternoon. The science stream would probably be more in my wheelhouse, dealing with GPU, maybe some molecular dynamics, something like that. If you guys have comments on anything I said today, because I know I said some stupid stuff, leave it down in the YouTube comment section or on Discord or whatever. I read that it's not real anymore, and it can now be represented as provability, so no collapse. Wait, what are we talking about? It's always frustrating when similar fields use the same name for different stuff, and the definitions is implied. Yeah. Jumping D to A or A to D requires a converter. Maybe avoid converting if possible. Well, yeah, but we're talking about so for the analog to digital in quantum, I think they're significantly different in that you don't have... You might be right. Maybe it is what it is. Maybe the D-Wave that's what they're doing. They're converting. Yeah, I need to learn. But I think I know enough that I have questions to ask to the person as I start talking to them. So I think that's fine. Okay, so anyway, tomorrow I'm going to come back. Again, I might do a writing stream in the morning. It would be Twitch only. And then in the afternoon, I transition into a science stream where we do, I think, probably GPU or maybe... tomorrow's Wednesday, isn't it? I thought tomorrow was Tuesday. Anyway, we'll do stuff tomorrow. I'm not entirely sure what I'm going to do, but it's something more I'm more interested in. Or I know more about. So guys, if you like the stream, feel free to let me know. I'm very interested in what you guys have to say. This is the first time I'm just trying to stream without I have a clear goal of what I'm doing every day, but it's quite different than what I used to do. And that I'm just kind of coming in, we're talking, we're chatting about sciencey things, and we're hoping that people are enjoying this, and taking part in the conversation. Man, I need some water. Man, my voice just got shot. Again, this is kind of coming off of how do I put this? This is coming off of a realization I've had recently that there just aren't enough researchers who are also making content online and who can have deep conversations about just academia and papers and stuff like this at a level where they can also describe that to other people. And so I'm not necessarily the best at explaining research concepts to people, but I figure we need more people who are at least trying, and that's what I'm doing. So this is what I'm trying to do. I'm just trying to have a conversation about actual research with, real people, and hope that this somehow, diffuses some tension in between, like, you know, I guess you could say academia and like normal people, because I'm feeling there's a lot of tension in the room. I'm feeling like a lot of people nowadays kind of like they just have this weird opinion on what academics are like, and they kind of feel like academic research is useless. And I just kind of want to be like that guy who stands in the middle and is like, yo, okay, look, academic research is not useless. Here's actually what the studies are doing, all this kind of stuff. So you're great at making analogies, so you hit that check mark of popularizing science for me, the layman. Hey, I really appreciate you guys being here. But that is it for today. Again, if you guys have any comments, questions, concerns, ideas, anything like that, let me know on YouTube, Twitch, whatever. I'm available everywhere. Look up Harvard Professor Quantum. Probably replaces it. All right, I can look it up. Harvard Professor Quantum. I don't typically, okay, maybe I'm a bit biased here, but because I work at MIT. Oh, you're talking about Lucan. Yeah, I've met Lucan. Is that who you're talking about? I mean, because I work at MIT, you know, like it's not that I have a bad opinion on Harvard. Harvard's great. It's just that, like, somehow we never, I tend to like prefer MIT people over Harvard just because I know the MIT people a bit better, you know? Look up Harvard Professor. Are we talking about Lucan? Or are we talking about a different Harvard professor? It's been a while since I met Lucan, though. I met him back at OIST. I don't really know so much. Like, a long time ago. I know he doesn't remember me. Okay, but another thing that I was thinking about doing recently is having conversations with like more researchers, like having a podcast or something like that. I don't know, where we just bring people who know what they're talking about on and we just talk about what they know. I have to find the YouTuber for the next time. Yep, anyway, guys, that's it for now. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Laos Labs. It will be tomorrow. We might do some writing and then some research. I'm not entirely sure, but we'll see you guys later. Bye, guys.